Consider this for a moment. There is a storm raging on a planet 550 million miles from Earth. And this storm is so vast, so powerful, so utterly alien, that it could swallow our entire world whole. Whole. Not just a city, not just a country, but the entire planet. Every ocean, every mountain, every continent you have ever known, every person you have ever loved, all of it, could be dropped inside this single atmospheric feature and still rattle around like a marble in a bathtub. This is the great red spot of Jupiter. And right away, we have to confront a paradox that shatters everything your gut tells you about weather. On Earth, a hurricane is a temporary, if terrifying, thing. It feeds on warm ocean water, it runs into land, it gets shredded by wind shear. Within a few weeks, at most, it is gone, a memory of chaos. But Jupiter's great red spot has been spinning for at least 350 years, maybe much longer. We are talking about a storm that has raged continuously since before the United States was a country, before the Industrial Revolution, before the invention of the steam engine. While Isaac Newton was still working out the laws of gravity, this storm was already old. The story of how we even know this is a detective story in itself, stretching back to the very dawn of telescopic astronomy. In the year 1610, Galileo Galilei turned his primitive spyglass toward the heavens and made a startling discovery. Jupiter had moons. He saw 4 of them dancing around the giant planet. But Galileo, for all his brilliance, did not record a great red spot. Maybe his instrument was too crude, or maybe, just maybe, the spot had not yet formed in a way we could recognize. The mystery deepens when we jump ahead to the year 1665. That is when a brilliant Italian astronomer named Giovanni Cassini, using a far superior telescope, recorded a dark permanent spot on Jupiter, a feature that seemed to persist year after year. And now we have to ask the billion-dollar question. Was that the same storm we see today? The evidence is tantalizing, but not certain. There is a gap in the historical record, a frustrating silence from the 1700s. Some astronomers think the spot faded, reformed, or changed colour. But a growing body of evidence suggests Cassini's spot is our spot, meaning this storm could be over 350 years old. And if that is the case, it means the Great Red Spot watched the entire Age of Enlightenment unfold. It was spinning away when Thomas Jefferson wrote the Declaration of Independence. It was churning when the Titanic sank. It has been alive for longer than any individual human being in recorded history. But what does that look like? What does 350 years of continuous wind actually mean? Let's talk about scale, because scale is the first thing that breaks your brain when you try to understand this thing. At its peak in the late 1800s, the Great Red Spot was absolutely enormous. It stretched across nearly 25,000 miles in width. To picture that, you have to stop thinking in terms of miles or kilometers and start thinking in terms of home. You could take 3 Earths, line them up side by side, and they would still barely stretch across the entire width of that storm. 3 Earths. That means the storm system itself, this swirling gyre of ammonia and broiling gas, was larger than the combined landmass of our entire planet, and it spun. For centuries. Even today, after some mysterious shrinkage that scientists are still debating, the storm is still well over 10,000 miles wide. It can still accommodate a single Earth with room to spare, but it is not just the size that terrifies. It is the wind. You have to compare it to our own worst nightmares to appreciate the difference. On Earth, a Category 5 hurricane is the absolute peak of nature's fury. The most powerful hurricanes on record, like Hurricane Patricia or Super Typhoon Haiyan, have sustained winds that push 400 kilometers per hour. That is fast enough to strip the asphalt off a road, to launch a car through a concrete wall, to level entire city blocks. It is apocalyptic. But the Great Red Spot? It laughs at 400 clicks. The outer edge of Jupiter's giant storm whips around at 640 kilometers per hour. That is nearly double the speed of the worst wind ever recorded on Earth. And unlike our hurricanes, which slow down when they hit land, the Great Red Spot has no land to hit. It has no friction. It just spins and spins, sustained by a planetary engine that we are only beginning to understand. So the central question becomes obvious. How? How does a storm survive for centuries? What is fueling it? What lies beneath that iconic, billowing, blood-red veil? For generations, this was one of the great unanswered questions in planetary science. We could see the top of the storm, the beautiful swirling clouds that looked like a Van Gogh painting come to life. But we could not see below it. It was like looking at a photograph of a murder victim and trying to guess the killer's motive. We had the surface, but we had no depth. And depth is everything. Then came the detective. In 2016, after a 5-year journey through the solar system, NASA's Juno spacecraft swung into orbit around Jupiter. This was not a casual flyby. Juno was built for a specific, brutal purpose. It was armoured. Jupiter is surrounded by the most intense radiation belts in the solar system, a hellscape of charged particles that would fry most electronics in minutes. Juno had a titanium vault, a radiation shield, to protect its brain. And it needed that brain intact, because Juno carried an instrument that would finally see through the clouds. It was called the microwave radiometer. Think of it as a deep space weather radar on steroids. It could peer beneath the colourful cloud tops down into the darker, hidden layers of the storm. And what it found in 2021, when the data finally came down, changed everything we thought we knew. For years, the leading theory was that the Great Red Spot was a relatively shallow feature, a kind of massive pancake of a storm that slid across the top of the atmosphere, like a spinning coin on a table. We base that on Earth logic. Our hurricanes, after all, are shallow creatures. They extend maybe 10 miles down into the troposphere, maybe 15 at the absolute max. They are a surface phenomenon. They die when they lose contact with the warm ocean. But Juno's microwave eyes saw something deeply different. The roots of the Great Red Spot, the actual structural base of this century-old monster, extend more than 300 miles deep into Jupiter's atmosphere. We are talking 500 kilometers. That is 30 times deeper than the entire depth of Earth's atmosphere. It is so deep that the storm is no longer just a weather event. It is a structural component of the planet itself. Let that sink in for a second. You have a storm that is not just sitting on top of the atmosphere. It is anchored into it. It reaches down into layers of Jupiter where the pressure is so crushing, the temperature so extreme, that ammonia and water behave in ways we can barely simulate in a lab. The storm is feeding on the internal heat of the planet. Jupiter radiates more heat than it receives from the sun, and that heat, rising from the deep interior, is the fuel. It is the gasoline for this eternal flame. The Great Red Spot is not just a cloud. It is a column, a deep, massive rotating cylinder of gas that extends a third of the way to the centre of the planet's gaseous envelope. And this changes the nature of the investigation. You are no longer asking, why does this hurricane last so long? You are asking a far more profound question. Is this storm alive in a way we do not fully understand? Because when you look at the data, you see that the storm has a metabolism. It has cycles. It pulses. It breathes. The storm shrinks and expands over decades. Its colour deepens and fades. Sometimes it seems to be dying, and then it roars back to life. In the late 1800s, it was enormous. By the time Voyager flew past in the 1970s, it was smaller. When Juno arrived, it seemed to be shredding, with red flakes peeling off the edge. Scientists held their breath, thinking the great storm might finally be giving up. But then, in the last few years, satellite imagery showed it starting to grow again, to puff up, to stand taller against the surrounding cloud bands. It is resilient, it is stubborn, it is almost willful. This brings us to final piece of the puzzle. The colour. Why is it red? For decades we had no clue. The clouds on Jupiter are mostly shades of white, beige and brown. But the Great Red Spot glows like a wound, a deep, rusty crimson that stands out against the pale bands of the planet. The most popular theory for a long time was that the red colour came from simple chemicals like phosphorus or sulphur, dredged up from the deep. But Juno's data, combined with laboratory experiments here on Earth, has pointed to a more exotic culprit. It is likely a cocktail of complex organic compounds. Think of it as a smog. The deep root of the storm is so energetic that it stirs up ammonia and acetylene, and then ultraviolet light from the sun breaks those molecules apart. They recombine into new larger molecules that happen to absorb blue light and reflect red light. It is a natural chemical factory. The spot is red because it is cooking its own planetary soot deep within its core. So we are left with a picture that is far stranger than anyone imagined 50 years ago. The Great Red Spot is not just a storm, it is a planetary engine, a massive, heat-driven, chemically active vortex that has been spinning for as long as human civilization has had telescopes pointed at the sky. Its roots go deeper than the ocean floor. Its winds are faster than any tornado. Its size, even as it shrinks, dwarfs the world we live on. And the most humbling part of this entire story is that we are only beginning to understand it. Juno's mission is not over. It is still circling Jupiter, still diving through that radiation belt, still sending back data that takes years to analyse. Every time we think we have the Great Red Spot figured out, it throws us a curveball. It shrinks. It grows. It changes colour. It sprouts new tentacles of gas. And that is the real hook, the real reason this storm captures our imagination. It is a mirror. We look at the Great Red Spot, and we see a force of nature that is utterly indifferent to us, that has been there since before we were a nation, that will likely be there long after we are gone. It reminds us that our planet, with all its fury, is small. Our storms are fleeting, but out there in the vast darkness, a red eye is watching, and it has been watching for a very long time. But the story does not end with the spot itself, because the environment that hosts this storm is as strange as the storm itself. Jupiter is not a solid world. It has no surface. When we speak of the Great Red Spot, we are speaking of a structure embedded in a fluid, a planet that is 90% hydrogen and helium, compressed into a metallic ocean under pressures millions of times greater than Earth's atmosphere. The storm is spinning in a medium that has no bottom. And that fact, the fact of a bottomless atmosphere, changes the rules of physics in ways that we are still trying to map. On Earth, a hurricane dissipates because it runs out of warm water, or because it hits a mountain, or because it encounters cold air. But on Jupiter, there is no mountain. There is no cold continent. There is only an endless, colourless abyss of hydrogen gas, slowly transitioning from a gas to a liquid, to a metal as you descend. The Great Red Spot does not encounter friction in the same way. It does not encounter boundaries. It is a vortex in a sea that goes on forever, or at least for tens of thousands of kilometres. It has no shore to crash against. It has no end, and yet even in this bottomless environment there are limits. The storm is not eternal. We know that because we have watched it change. The Voyager flybys in 1979 gave us our first clear close-up images of the spot. It was a beautiful, complex, turbulent maelstrom. But when we compare those images to the ones taken by the Hubble Space Telescope in the 1990s, and then to the ones taken by Juno in the 2010s, we see a clear trend. The spot is shrinking. It is not a steady shrink, but an overall one. In the late 1800s, it was 25,000 miles across. By the time Voyager arrived, it was about 14,000 miles across. By the time Juno arrived, it was barely over 10,000 miles across. That is a loss of more than half its width in a little over a century. And it is not just shrinking in width, it is also becoming more circular. Historically, the spot was an elongated oval, stretched out like a football. Now it is rounder, more compact, as if it is condensing. Scientists have wondered if this means the storm is dying, or if it is simply settling into a new equilibrium. The answer seems to be tied to the deep structure we discovered. Because the storm is anchored so deep, it is not just a surface swirl. It draws energy from the deep atmosphere, from the planet's internal heat. But that deep reservoir may not be infinite. There may be a limit to how much energy the storm can extract from the depths. And as it interacts with the surrounding jet streams, the massive bands of wind that stripe Jupiter, it loses energy to them. The storm is locked in a battle with the planet itself. The jet streams push against it, trying to tear it apart. The deep heat feeds it, trying to sustain it. And we are watching that battle play out in real time, over decades and centuries. It is a slow-motion war, and we do not know who will win. But there is another layer to this mystery, one that touches on the very nature of how we understand weather. On Earth, we have a concept called the Rossby number. It is a measure of how much the rotation of a planet influences a fluid flow. The Great Red Spot exists in a regime where the Coriolis force, the force that makes hurricanes spin on Earth, is dominant. Jupiter rotates once every 10 hours. That is the fastest rotation of any planet in the solar system. That incredible spin creates powerful vortices at the boundaries between the jet streams. And the Great Red Spot is the mightiest of those vortices. It sits between two opposing jet streams, one flowing east, one flowing west. It is caught in a trough, a zone of shear that both confines it and feeds it. It is like a massive ball bearing spinning between two conveyor belts. The belts push it, and it spins, and it has been spinning so long that it has created its own microclimate, its own internal structure. Inside the spot, there are smaller vortices. We see them in the imagery, little white ovals, smaller storms that rotate around the central red core. They are like moons orbiting a planet. Sometimes they merge with the main spot. Sometimes they are ejected. Sometimes they grow and become independent. The Great Red Spot is not a solitary monster. It is a system. A complex, dynamic, chaotic system that has been evolving for centuries. And every time we think we have catalogued all its behaviours, it surprises us. In 2019, scientists noticed that the spot was flaking. Sheets of red gas were peeling off its western edge, drifting away like banners in the wind. It looked like the storm was shedding skin. No one had predicted that. It was a brand new phenomenon, seen for the first time after centuries of observation. That tells you how much we still do not know, and that unknown is the most humbling part. We have sent spacecraft to Jupiter. We have parked a probe in orbit around it. We have spent billions of dollars and decades of human effort to understand this one storm, and we still cannot predict what it will do next year. We cannot tell you why it turned red. We cannot tell you if it will be there in 1,000 years. All we can do is watch and measure and wonder, and that is why the Great Red Spot remains one of the greatest natural wonders in the solar system. It is a reminder that even in the age of science, even with our most advanced instruments, nature still holds secrets. The red eye gazes at us from across 500 million miles of empty space, and it tells us nothing. It just spins. It has been spinning since before we were a nation. It will spin long after we are a memory, and we are still trying to guess why. We knew it was big. We knew it was red. And we knew, with a certainty that felt almost smug, that it had been there for a very, very long time. But before the Juno spacecraft arrived to shove our assumptions into a blender and hit puree, the Great Red Spot was a giant, beautiful, infuriating question mark painted onto the face of a god. This is where we were. This is the puzzle we had stared at for over a century, armed with telescopes, flybees, and a whole lot of educated guessing. Let us paint the picture with what we had. From Earth, even through the best telescopes of the 20th century, the Great Red Spot looked like a lazy floating eye, a pinkish oval blemish in Jupiter's southern hemisphere, and we could see it was moving. It was not stuck, it was drifting slowly, like a raft on an ocean of hydrogen and helium. That drift, that rotation, was one of the first hard numbers we pinned down. This thing spins counterclockwise. It takes just under 6 Earth days to complete one full rotation. Think about that for a second. A storm the size of a planet, and it spins slower than a work week. But do not let that slow spin fool you. That counterclockwise motion meant one thing, loud and clear. This was not a blemish. This was an anticyclone, a high-pressure system. On Jupiter, that is the definition of majesty. And then, in 1979, we got our first real close-up. Voyager 1 was screaming past the Jovian system, a robotic postcard from humanity, and it snapped the first image that made the whole world lean in. The storm was not just a red oval, it was a churning, chaotic, violent mess. The edges were not clean lines, they were tangled strands of gas, filaments that looked like wisps of torn silk caught in a hurricane. The centre was calm, eerily calm, but the outer bands were a battleground. Clouds smashed into each other at speeds that would shred a mountain on Earth. And right there, trailing south of the big red beast, Voyager spotted something else. A tiny white oval. Just a little puff of a storm, barely worth a footnote at the time. That white oval, oh, we know it now. It was a baby. A precursor to what would later become Oval BA, the storm that would eventually blush from white to red and give us a whole new headache to worry about. But in 1979, it was just a curiosity. Voyager did not just take pretty pictures. It had infrared eyes, and those eyes saw something that made the scientists scratch their heads. The centre of the great red spot was warm. Not just a little warmer, measurably warmer than the storm's jagged edges. That was a slap in the face to the simple models. A storm, any storm, should be cold at its core if it is just a weather event on top of a cold atmosphere. But this core was hot. That heat suggested that the storm was not just a surface feature. It was tapping into something deeper. There was a heat source beneath it. An internal engine. The storm was not just blowing wind. It was pumping heat up from the planet's interior. That changed the game. We were no longer looking at a cloud. We were looking at a thermal chimney, a conduit for Jupiter's own internal fire. Then there were the walls, the jet stream walls. Imagine the most powerful river on Earth. Now imagine two of them running in opposite directions, flanking a single enormous whirlpool. That is what Jupiter does to the Great Red Spot. On its northern side, a massive eastward jet stream screams past at nearly double the speed of the storm's own rotation. On its southern flank, a westward jet stream roars in the opposite direction. These are not gentle breezes. They are atmospheric highways, moving at hundreds of miles per hour, and they act as gravitational containment. They lock storm in place. Think of them as the canyon walls that force the river to stay in its channel. The storm wants to drift. It wants to wander, but those jet streams grab its edges and squeeze. They keep the monster caged. Without those jets, the Great Red Spot would have dissipated centuries ago. They are the reason we have a mystery to solve at all. But all of this, the spinning, the heat, the jet stream walls, was just the warm-up for the main course. The shrinking. This is where the human brain starts to bend. We had observations stretching back to the 1800s. Old astronomers, squinting through glass, drawing sketches in notebooks. They recorded the size of the red spot with remarkable consistency. In 1879, those observers measured the storm at roughly 41,000 kilometers across. 41,000. That is wider than the entire planet Earth. The red spot at that time could have swallowed our world whole with room to spare for a small moon or two. It was the undisputed king of storms. Now, fast forward to the space age. We start taking precise measurements. The Hubble Space Telescope, launched in 1990, gave us a front row seat that never expired. From 1995 to the early 2020s, Hubble watched. It clicked. It measured. It confirmed something that made the old astronomers spin in their graves. The storm is shrinking, not a little, a lot. By the time Juno arrived, the Great Red Spot measured just 16,000 kilometers across, from 41 to 16. That is a loss of over 60% of its width in just over 100 years. It is like watching Godzilla slowly shrink into a lizard. The storm is not just changing shape. It is deflating. It is folding in on itself. Or at least, that is what it looked like from a distance. This shrinkage forced a brutal question on the scientific community. Is this the natural life cycle of a Jovian giant, or are we watching it die? Some argued it was just contracting vertically, getting taller as it got narrower. Others feared the worst, that the storm we obsess over is a fading echo of its former self, a superstorm running out of gas. Hubble's data showed that the shrinking was not linear. It sped up in the 1990s and then slowed down again. The storm is stubborn. It does not want to go quietly, but the trend line is unmistakable. The monster is getting smaller, and then there is the colour. Oh, the colour. This is where the guessing really got wild. The Great Red Spot is red. That is its whole identity. But what makes it red? That question haunted planetary scientists for decades. Before Juno, we had a dozen theories and not a single answer. The simplest idea was sulfur. Jupiter's atmosphere is loaded with sulfur compounds. Maybe lightning deep in the storm was breaking those compounds apart, painting the clouds red like a giant chemical crayon. Good guess. But it had problems. The colour was not matching pure sulfur spectra. It was too dark, too organic. Then came the tholins, and if you want a word that sounds like it belongs in a sci-fi novel, tholins is it. These are complex organic molecules, formed when simple gases like methane and ammonia get bombarded with ultraviolet radiation from the sun. The lab results were tantalizing. If you zap those gases with UV, you get a reddish-brown goo. Tholins are found on the surface of Pluto, on Titan, on comets. They are basically the universe's crude oil. So the theory went. The Great Red Spot was a vat of Jovian atmosphere cooking in the sun, producing a smear of organic sludge. Beautiful idea. But again, the spectra were not a perfect match. Close, but not quite. Then came a breakthrough in 2014. A team of scientists decided to run a very specific experiment. They took ammonia and acetylene, two gases known to be abundant in Jupiter's upper atmosphere, and they blasted them with ultraviolet light. The result was a deep, rich red, a colour that, for the first time, matched the observed spectrum of the Great Red Spot almost perfectly. The conclusion was stunning. The red was not from deep volcanic vents. It was not from exotic chemistry in the core. It was a sunburn, a chemical sunburn. The storm rises so high above the surrounding cloud decks that it pokes its head into the upper atmosphere, where the sun's ultraviolet rays are merciless. That constant UV bombardment cooks the ammonia and acetylene, polymerizing them into a reddish-brown chromophore, the colour-producing substance, the chromophore. That became the leading hypothesis. But here is the kicker, and this is the part that kept us humble before Juno arrived. The colour is a surface phenomenon. It is a skin, a thin, fragile layer of sun-damaged molecules sitting on top of a much deeper, much cooler storm. It is like the tan on an old sailor. The real action is beneath that skin, and we had absolutely no clue what that action was. We knew the heat was there. We knew the jets were there. We knew the storm was shrinking, but we did not know why it was red in any definitive mathematical way. We had the lab experiment. We had the supporting data from Earth-based telescopes. But we lacked the close-up, the taste test, the direct measurement. We were diagnosing a patient by looking at its shadow. This is the sum of human knowledge as Juno began its final approach. We had a storm that spun counterclockwise every 6 days. We had Voyager's images of chaos and filaments. We had a tiny white oval that would grow up to become a red sibling. We had infrared images showing a hot core. We had atmospheric walls that kept the beast contained. We had a 100-year history of alarming shrinkage. And we had a leading theory that the red colour was a chemical sunburn, a chromophore cooked by UV light. But no one had ever sampled it. That was the state of play. We were confident. But confidence is not the same as truth. The Great Red Spot was the most photographed, most measured, most debated storm in the solar system, and yet it refused to give up its deepest secrets. Every new observation only raised new questions. Why is it hot at the centre? How deep does the red go? Is the shrinkage accelerating or decelerating? Is there a solid core of water or ice beneath the tops? We had models, we had simulations, but models are just educated fantasies until you shake hands with the data. And the data, as of the early 21st century, left us with more mystery than certainty. So this is the stage. This is the scale of human puzzlement. We had built a cathedral of knowledge, but its foundation was sitting on sand. The storm was a monument to our ignorance. And that is a beautiful thing, because it means that every answer we get is a revolution. We knew the storm's shape, we knew its motion, we knew its colour, but we did not know its soul. And that is exactly where Juno was about to step in. The spacecraft was built to pierce the veil, to fly directly into the heart of that crimson eye, to measure its depth, to taste its chemicals, to finally answer the question that had been whispered in observatories for over a century. Are we right, or are we fools? The answer, as you might suspect, was a little bit of both. The uncertainty surrounding the Great Red Spot was not just a scientific problem. It was a philosophical one. We had built an entire career out of studying this single atmospheric feature, and yet, when the math was done, we realized we did not even know how it breathed. The storm rotates, yes, but a storm does not simply hang in the air, it consumes energy. It dissipates energy. It must have a metabolism. On Earth, hurricanes are fed by warm ocean water. They draw heat from the surface, and that heat drives their fury. Jupiter has no ocean, at least not the kind we understand. So what fuels the Great Red Spot? This was the question that haunted every paper, every conference, every late night in the office. One theory proposed that the storm was a deep convection cell, a giant bubble of warm gas rising from Jupiter's interior. As the gas rises, it cools, condenses, and releases latent heat. That heat then powers the storm's rotation. This is how a tropical thunderstorm works on Earth, but scaled up to planetary dimensions. The problem was that Jupiter's internal heat, while real, is not evenly distributed. The planet radiates more heat than it receives from the Sun. That is a settled fact. But how much of that internal heat gets funneled into a single storm? No one could say. The numbers did not add up. The energy required to keep a storm the size of Earth spinning for centuries, if not millennia, was staggering. If the Great Red Spot were a simple heat engine, it would have needed an energy source equivalent to thousands of nuclear power plants running continuously, and we had no evidence of that kind of energy concentration. Another school of thought argued that the storm was not powered from below, but from the sides. The jet streams, those roaring walls of wind, could be injecting energy into the system. As the storm rubs against these jets, it could be acting like a giant gear, catching the kinetic energy of the planetary circulation and converting it into rotational energy. This would make the Great Red Spot a parasite, a vacuum cleaner attached to the fastest winds in the solar system. It would not need its own internal engine, it would just siphon energy from the environment. This was an elegant idea, but it had a fatal flaw. The jet streams are not infinite batteries. If the storm is draining them, they would slow down. Yet the jets remained stubbornly fast. Either the system was perfectly balanced, or we were missing a major piece of the puzzle. And then there was the question of the storm's lifetime. How old is it? We had observed it for over 150 years, but surely it had existed before we invented the telescope. Some astronomers argued that the Great Red Spot was a permanent feature of Jupiter, a fixed mark on the planet's face that had been there since the gas giant formed. Others pushed back, pointing out that a storm cannot be permanent on a planet that changes its appearance every few days. Jupiter's cloud bands shift, its colours fade and brighten. Nothing is static. The red spot had to have a birth date, but when? And what caused it? In 2018, a team of researchers made a bold claim based on historical observations. They argued that the Great Red Spot we see today is not the same storm that Giovanni Cassini observed in the 17th century. Cassini, a brilliant Italian astronomer, had spotted a dark oval on Jupiter in 1665. He called it the permanent spot, and he tracked it for decades. That spot vanished in the early 18th century, completely gone. Then, in the late 19th century, a new spot appeared, a red one. The researchers argued that the original Cassini spot was a completely different atmospheric feature, and the modern Great Red Spot is a teenager, geologically speaking. A storm born only about 400 years ago, a millennial storm, but not an eternal one. This idea was controversial. It suggested that giant anticyclones on Jupiter come and go, forming and dissolving over centuries. It made the Great Red Spot less of a monument and more of a temporary guest. But it also raised the stakes. If storms like this can form relatively quickly, then Jupiter is far more dynamic than we ever imagined. There could be monsters hiding in the depths, waiting to emerge. While the historians debated the origin, the chemists were still arguing about the colour. The UV-bombarded ammonia theory was the frontrunner, but it was not a unanimous victory. A persistent minority insisted that the red colour was caused by phosphorus compounds. Phosphorus, when exposed to radiation, turns red, and Jupiter's atmosphere contains trace amounts of phosphine. This gas smells like garlic and is highly toxic, but it is a real component of the Jovian chemistry. The phosphorus camp pointed out that the UV ammonia theory required acetylene to be present in high concentrations, but the actual measurements of acetylene in the storm were inconsistent. Sometimes it was there, sometimes it was not. The phosphorus theory, on the other hand, explained why the storm's red colour deepens during periods of increased solar activity. Phosphine is unstable, it decays quickly. If the sun flares up, more ultraviolet light could break down more phosphine, darkening the red. It was a plausible alternative that refused to die. The stalemate was broken only by the recognition that we needed in situ data. We needed to know exactly which molecules were hanging in the storm's upper atmosphere. We needed to know the temperature at multiple altitudes. We needed to know the nature of the particles that scatter the light. And that is precisely what Juno was built to deliver. The spacecraft carried an instrument called GIRAM, the Jovian Infrared Auroral Mapper. It was designed to peer through the cloud tops at infrared wavelengths. It could see heat. It could see chemicals. It could map the internal structure of the Great Red Spot in a way that Voyager and Galileo could only dream of. But there was a terrifying risk. The storm might not be what we hoped. The most dangerous thing in science is to fall in love with your hypothesis. And humanity had fallen deeply in love with the idea of the Great Red Spot as a deep, ancient, structured beast. We wanted it to be a root system stretching thousands of kilometers into the planet. We wanted it to be a monument to Jupiter's primordial power. But what if it was shallow? What if the storm was just a thin skin of spinning clouds, barely more than a few hundred kilometers deep, sitting on top of a calm atmosphere? That would be a letdown. But it would also be a truth. Juno was about to perform an autopsy on the most famous storm in the solar system, and no one knew if the patient had any vertical depth at all. The stage was set. The tensions were high. The scientific community had spent a century weaving a tapestry of theories, guesses and assumptions. Now the spacecraft was about to thread the needle. In July 2017, Juno made its closest approach to the Great Red Spot. It flew directly over the storm at an altitude of just 9,000 kilometers above the cloud tops. The instruments were running. The data stream was active. The entire world of planetary science held its breath, and when the first numbers came back, they were not what anyone expected. The storm was deep, much deeper than the most optimistic models had predicted. The roots of the Great Red Spot extended down to depths of at least 300 kilometers below the cloud tops. Possibly deeper. That changed everything. The storm was not a superficial swirls. It was a column of organized chaos, anchored deep in Jupiter's hydrogen envelope. The discovery of the storm's depth solved one mystery and created another. How could a weather system remain coherent over such a huge vertical distance? On Earth, convection is limited by the tropopause. Storms hit a ceiling. Jupiter has no solid surface, no hard boundary. The atmosphere just gets denser and denser as you go down. The red spot had to be penetrating this dense interior, displacing massive amounts of gas. The force required to maintain that structure was beyond comprehension. It meant that the storm's energy was not just coming from the sides or the top. It had to be drawing power from an enormous reservoir of heat below. And that is where the story stands at the turning point. The Juno data was still being processed. Every new orbit brought new revelations. The storm was a mystery that had refused to give up easily. But we had finally broken through the first wall. We had confirmed that the Great Red Spot was not a ghost. It was a living, breathing, three-dimensional giant, anchored in the depths of Jupiter like a mountain in the sky. The journey from Cassini's dark oval to Juno's thermal map had taken 400 years, and we were only just beginning to understand what we were looking at. July 11th, 2017. Mark that date, because on that day a piano-sized piece of human engineering did something no machine had ever dared to do. It took a dive. Not into water, not into rock, but into the heart of an atmospheric abyss so vast that entire Earths could be swallowed whole without a trace. Juno, NASA's solar-powered warrior, was about to make its closest flyby over the Great Red Spot. And I mean closest. We're talking a mere 9,000 kilometers above the storm's roiling top. That's not even the height of a long-haul airplane flight, relative to the scale of this planet. It was a death-defying kiss with chaos. But you have to understand this wasn't a whim. This was a calculated, meticulously planned act of scientific courage. For months, the mission team had been waiting for this exact moment. Jupiter's great red spot had been taunting us for centuries. We had sketched it, photographed it, watched it shrink and change colour, but we had never truly touched it. Juno was built for this. The spacecraft is a beast of contradictions. It looks fragile, with those 3 enormous solar arrays stretching out like the blades of a windmill, each one as long as a school bus. But inside that hexagonal body lies a secret. A titanium vault, nearly a centimetre thick, wrapped around the mission's brain. Why? Because Jupiter isn't just a planet. It's a radiation nightmare. The magnetic field is a death trap, spitting out particles with enough energy to fry an unprotected computer in minutes. That vault, weighing over 170 kilograms of pure armour, is why Juno is still alive. It's a tiny, armoured submarine sailing through a hurricane of fire. And the orbit. God, the orbit. Juno doesn't just sit there like a geostationary satellite. It's on a highly elliptical 53-day loop. That means it swings far away from Jupiter, where it's safe, collects its data, and then, like a roller coaster hitting the drop, it plunges back in for a few hours of intense, frantic science. That's all the time it gets, a few hours every 53 days to stare into the abyss. And on July 11th, 2017, the abyss stared back. Let's talk about the tools, because this wasn't just a flyby for pretty pictures. Juno carried a set of instruments that turned the spacecraft into a floating laboratory. The most important one for this job was the microwave radiometer, or MWR. Think of it as a set of eyes that can see through walls, except the walls are made of ammonia clouds, thousands of kilometers thick. The MWR operates at 6 different frequencies, each one tuned to peer at a different depth. It's like Earth's weather radar on steroids, but instead of rain, it's mapping the temperature and composition of gas at hundreds of kilometers down. The team calls it a thermal X-ray. It doesn't just take a picture, it takes a temperature scan of Jupiter's internal organs. And then there's the gravity experiment. This one is pure poetry. You don't measure gravity on Jupiter with a spring scale. You do it by tracking Juno's radio signal. As the spacecraft flies over the Great Red Spot, the storm's enormous mass pulls on Juno. Just a little. That pull changes Juno's velocity by a fraction of a hair. We're talking about Doppler shifts of 0.05 millimeters per second. That's slower than a snail moving through peanut butter. But the team on Earth can detect that. They can feel that tiny tug. And from that tug, they can weigh the storm. They can calculate how much mass is moving underneath. Like a doctor feeling a lump beneath the skin. So, what did Juno find when it finally stuck its nose into the storm? Let's start with the MWR. The data came back, and the scientists probably needed a stiff drink. The models, our beautiful computer simulations of how a storm should work, were completely wrong. We expected a uniform structure, maybe a cold core at the top, getting warmer as you go down. That's how hurricanes work on Earth. The eye is cold and calm, surrounded by a wall of warm, violent air. But Jupiter doesn't play by our rules. The MWR saw a temperature structure that was chaotic. It found warm cores buried deep inside the storm, pockets of anomalous cold regions that shouldn't exist. It was like finding a patch of ice in the middle of a burning building. And the depth. God, the depth. The old assumption was that the Great Red Spot was a shallow phenomenon, maybe 100 kilometers deep, like a big cloud floating on top of a liquid hydrogen ocean. Juno laughed at that. The data showed that the storm's roots extend at least 500 kilometers down, maybe deeper. The signals from the MWR just kept going. The warm anomalies persisted all the way to the limit of the instrument's vision. This storm isn't a cloud. It's a column of energy, a giant hungry mouth reaching deep into the planet's belly. 500 kilometers. For context, Earth's entire atmosphere is about 100 kilometers thick. Jupiter's storm digs a hole 5 times deeper than our sky is tall. Then came the gravity data. Remember the tiny tug on Juno? It was there. The spacecraft's trajectory was perturbed. That means the storm has measurable mass. It's heavy. It's pulling on Juno like a giant underwater whirlpool pulling a boat. The gravity signature was so clear, so distinct that the team could map the storm's shape in 3 dimensions. It bulges at the top like a mushroom, but it narrows into a long, twisting trunk as it goes down. It's not a cylinder, it's a cone. An upside-down, slowly rotating cone of chaos, anchored somewhere deep in Jupiter's interior. But here's where the story gets weird, really weird. The GIRAM instrument, the infrared imager, took a thermal portrait of the storm, and what it saw was like nothing in any textbook. Instead of a smooth, uniform red eye, GIRAM revealed spiral bands. Bands of alternating warm and cold gas, swirling around the center like a spiral staircase. This was not predicted. Think of a hurricane on Earth. You have the eye wall, and the rain bands. It's messy, but it's structurally simple. Jupiter's storm had layers. It had structure. It had complexity that we still, to this day, do not fully understand. It was like looking at a human brain instead of a simple bruise. And the heat. Oh, the heat. This is the part that keeps astrophysicists up at night. The Great Red Spot is not just spinning. It's generating its own heat. It's a self-licking lollipop of thermal energy. We call it a heat engine in reverse. On Earth, a hurricane is powered by the warm ocean. The heat from the water evaporates, rises, condenses, and releases energy. It's an external process. Jupiter has no ocean. There's no warm water to fuel this beast. Yet the storm is hotter than its surroundings. Not by much, but enough to matter. Enough to suggest that the storm is pumping energy from deeper layers up to the cloud tops. It's like a well that doesn't need a pump. It just keeps flowing. Contrast that with Earth. An Earth hurricane is a dissipating machine. It needs constant fuel. The moment it hits land, it dies because the fuel supply is cut off. Jupiter's storm is the opposite. It hasn't died in 400 years. It might be 1,000,000 years old. It might be older than humanity. It exists in a state of almost perfect self-sustenance. The data suggests that the storm is actively pulling heat from Jupiter's interior, from the deep, hot layers where the pressure is millions of times Earth's atmospheric pressure. It's mining the planet's own internal heat, and then it pushes that heat upward, creating the violent, turbulent clouds we see from space. This changes everything. It means the Great Red Spot is not a weather event in the way we understand weather. It's a geological feature. It's an atmospheric mountain, but it's also a furnace. It's alive in a way that a hurricane on Earth can only dream of being. The storm is feeding on Jupiter itself, and the planet doesn't seem to care. The energy cycle is so efficient, so perfectly tuned, that the storm maintains itself with minimal loss. It's the perfect perpetual motion machine, but only because Jupiter has an infinite fuel tank. The surreal implication is hard to swallow. The Great Red Spot is self-sustaining. It doesn't need a trigger. It doesn't need a seasonal change. It just exists, humming along in the deep red twilight of Jupiter's atmosphere, recycling energy from the planet's scalding core to the frozen cloud tops. It's a bridge between the surface and the abyss, and we flew through that bridge. Think about the scale of that moment. 9,000 kilometers above the clouds. Juno, a tiny robot from Earth, screaming through the outer rim of a self-powered vortex that dwarfs continents. The MWR is clicking, taking temperature readings every millisecond. The gravity team is holding their breath, watching the radio signal flicker. The GIRAM camera is snapping infrared images of spiral bands that no human eye has ever seen. And the storm just keeps spinning. It doesn't care. It doesn't even notice. The data from that single flyby rewrote entire chapters of planetary science. We used to think of gas giants as simple, layered balls of gas. Now we know they are complex, dynamic, almost biological in their behavior. The Great Red Spot is not just a storm. It's a symptom. It's a visible manifestation of the massive churning engine that is Jupiter's interior. It's the planet's heartbeat, visible from space. And we only got one good look. One single, perfect flyby. The team knew they had to get it right. Every parameter had to be nailed. The orbit was planned months in advance. The instruments were calibrated to within an inch of their lives. And when the data finally streamed back to Earth through the vast silent void, the team saw the truth. The storm was deeper than thought. It was hotter than thought. It was more organized than thought. It was in every way more than we expected. The journey from Cassini's dark oval to Juno's thermal map had taken 400 years. But on July 11, 2017, we didn't just look at the storm. We touched it. We felt its weight. We measured its heat. We saw its roots. And we realized with a mixture of awe and humility that the Great Red Spot is not a feature of Jupiter. It is Jupiter. It is a part of the planet's soul, visible to anyone who cares to look. And the only reason we found this out is because we had the guts to send a robot into the abyss, protected by a titanium shell, powered by the sun, and guided by the insane ambition to know. The implications of that self-sustaining heat engine are staggering. When Juno's microwave radiometer saw those warm anomalies descending 500 kilometers into the abyss, it forced us to reconsider the entire architecture of the planet. Jupiter's interior is not a placid, stratified ocean of hydrogen. It is a turbulent, churning sea where energy flows in ways we barely understand. The Great Red Spot is not a passive scar on the skin. It is a siphon, a conduit, a direct pipeline connecting the visible cloud deck to the deep, pressurized interior where hydrogen turns into a metallic fluid under millions of atmospheres of pressure. That heat has to come from somewhere, and the only source deep enough to sustain a storm of this magnitude for centuries, perhaps millennia, is the primordial heat left over from Jupiter's formation. The storm is literally powered by the birth of the solar system. But there is a darker, more unsettling possibility. The heat might not be left over, it might be actively generated. Deep inside Jupiter, the pressure is so immense that hydrogen behaves like a metal. It becomes a conductor. And in the presence of Jupiter's ferocious magnetic field, that metallic hydrogen generates electric currents. Those currents produce heat. It is possible, though not yet proven, that the Great Red Spot is tapping into that electromagnetic energy. Imagine an atmospheric storm that is not powered by sunlight or ocean heat, but by the planet's own magnetic dynamo. It would be a weather system with a power source that is fundamentally alien to anything on Earth. It would be a storm that draws its energy from the same invisible forces that create the auroras. The Great Red Spot might be a magnetic storm masquerading as a weather system. Let me take you back to the historical context to understand how far we have come. 4 centuries ago, in 1665, the Italian astronomer Giovanni Cassini first described a permanent spot on Jupiter. He called it the permanent spot. He watched it drift, change shape, and persist. He had no idea what it was. He had no telescopes powerful enough to see its structure. He simply recorded its existence. For 200 years it was a curiosity. Then, in the 19th century, better telescopes revealed its reddish colour. People began to call it the Great Red Spot, but they still had no explanation. Some thought it was a solid body floating in the atmosphere. Others believed it was a giant mountain poking through the clouds. The truth was so far beyond their imagination that they could not even guess. In the 20th century, the Pioneer and Voyager spacecraft gave us the first close-ups. They revealed the spot's true scale. It is a storm larger than Earth. They show to us its counterclockwise rotation, the swirling cloud bands, the turbulent wake behind it. But they only saw the surface. They could not see beneath. Voyager's instruments were brilliant for their time, but they were blind to depth. For 30 years, we lived with the assumption that the storm was a shallow cloud feature, maybe 50 kilometers deep. It was a hurricane, just a really big one. That assumption was comfortable. It fit our models. It did not challenge our understanding of fluid dynamics. Then came Juno. And Juno did not just challenge the assumption. It obliterated it. 500 kilometers. Not 50, not 100, 500. The storm does not float on the surface. It dangles from it like an anchor chain. The roots of the storm reach into a region where the pressure is tens of thousands of times Earth's atmospheric pressure. The temperature there is thousands of degrees. And yet the storm maintains its structure. It does not dissipate. It does not get torn apart by the sheer forces of the deep atmosphere. It remains coherent. It remains organized. It is as if you dropped a spoon into a pot of boiling water and the spoon continued to stir itself for 400 years. This raises a profound question about stability. How does a structure that is 500 kilometers tall, rotating at hundreds of kilometers per hour, remain stable in an environment that is violently turbulent? The answer, suggested by Juno's gravity data, is that the storm is held together by its own weight. The column of gas is denser than the surrounding atmosphere. It sinks. It is heavier. It is like a block of lead in water. It wants to fall, but the rotation keeps it suspended. The Coriolis force, the same force that makes hurricanes spin on Earth, wraps around the dense column and locks it in place. The storm is a balancing act between gravity and rotation, and it has been balancing for longer than the United States has existed. Let us talk about the colour, because that is the most visible mystery. Why is it red? Juno's gyrum instrument, which sees in infrared, gave us clues. The red material is likely a combination of sulfur, phosphorus and organic compounds. But the exact chemistry is still debated. What Juno showed us is that the red material is not uniformly distributed. It is concentrated in the centre of the storm, in the eye. The outer bands are paler, almost beige. This suggests that the red colour is a product of the storm's internal chemistry. The deep upwelling brings material from hundreds of kilometres down, material that has been exposed to extreme pressure and radiation. When that material reaches the cloud tops, it reacts with sunlight and produces the red pigment. The storm is not just stirring gas. It is acting as a chemical factory, synthesizing compounds that are unique to its interior. And there is a terrifying implication in that. If the red colour is produced by the upwelling of deep material, then the colour itself is a tracer. It tells us that the storm is actively mining Jupiter's interior. Every red photon we see is evidence of a connection between the surface and the deep. The storm is a window into the planet's soul, and that window is painted red with the blood of Jupiter's interior. Consider the recent changes. In the past decade, the Great Red Spot has been shrinking. Observers on Earth have watched it contract. It is smaller now than it has been in recorded history. Some thought it was dying, but Juno's data tells a different story. The storm might be shrinking in width, but it is not losing depth. The roots are still there. The internal structure is still intact. It is as if the storm is pulling itself together, becoming denser, more concentrated. It is not dying. It is compressing. It is becoming a tighter, more intense vortex. The shrinkage might be a sign of maturity, not decay. The storm might be entering a new phase of its existence. The data from Juno's flyby also revealed something about the storm's influence on the rest of the planet. The Great Red Spot is not an isolated feature. It generates waves. Atmospheric waves, like ripples in a pond, radiate outward from the storm for thousands of kilometers. These waves propagate through the cloud decks, interacting with the bands and zones that stripe the planet. The storm is a driver of weather across the entire southern hemisphere. It is a pacemaker for Jupiter's atmosphere. When the storm changes, the whole planet feels it, and we are only beginning to map those connections. There is a moment in the mission that the engineers remember vividly. The flyby was programmed with a margin of error of a few seconds. The spacecraft had to execute a precise turn to point its instruments at the storm. One wrong angle, one timing error, and the data would be worthless. The team had rehearsed the sequence dozens of times on simulators, but when the actual signal arrived, there was a delay, a long one. The radio waves took 48 minutes to cross the distance between Jupiter and Earth. That meant that by the time the team knew the flyby had started, it was already over. The spacecraft was already on the other side of the storm, already sending its precious data. There was nothing they could do but wait and hope. The data came in slowly. The downlink speed from Juno is not fast. It is a trickle. The spacecraft is so far away that the signal is weak. It took days to receive the full set of measurements. The scientists sat in front of their screens, watching numbers appear one by one. The first hints came from the radio signal itself. The Doppler shift was there. The gravity team saw it immediately. The storm had mass. Then the MWR data started to arrive. The first warm anomaly showed up at a depth of 200 kilometers, then another at 300, then another at 400. The team realized they were looking at something no one had ever seen before. They were reading the internal temperature profile of an alien weather system. It was like seeing a patient's X-ray for the first time. And there was a moment, captured in the mission control room, when the lead scientist looked at the screen and simply said, "It's deeper than we thought." That was the understatement of the century. It was deeper than anyone had thought possible. It was deeper than the models allowed. It was deeper than physics should permit for a storm in a gas giant. But there it was. The data does not lie. Let me tell you about the atmospheric entry probe that never was. In the 1990s, NASA considered sending a probe directly into the Great Red Spot. The idea was to release a small capsule that would parachute down through the storm, measuring temperature, pressure, composition, and wind speed all the way to the bottom. It was a beautiful concept. The probe would have been a direct descendant of the Galileo probe that entered Jupiter in 1995. But Galileo's probe went into a dry, hot spot, not the storm. It survived for about an hour before being crushed and vaporized. A probe into the Great Red Spot would have faced violence beyond imagination. The wind speeds in the storm are over 400 kilometers per hour. The turbulence would have torn the parachute. The pressure would have crushed the electronics. The heat would have melted the casing. The mission was deemed too risky. It was shelved. But Juno is the next best thing. Juno does not enter the storm. It flies over it. It uses its instruments as a remote stethoscope. It listens to the storm's heartbeat from a safe distance. And it has told us more in a few hours than a probe could have in a few minutes. The trade-off is worth it. We have a map of the storm's interior without having to sacrifice a spacecraft. The science is far from complete. The Juno mission is still ongoing. It has completed dozens of orbits. Each pass over the Great Red Spot adds new data. The team is building a time-lapse of the storm's internal evolution. They are watching it breathe. They are watching it pulse. They are watching it live and die and live again. The storm is not static. It changes. It shudders. It exhales plumes of ammonia and water vapor. It inhales surrounding cloud bands. It is a creature of rhythm and cycle, and we are only beginning to understand its language. The microwave radiometer has revealed that the storm has a heartbeat, a thermal pulse. The temperature at the base of the storm oscillates on a timescale of weeks. It is not constant, it flickers. The team does not know why. It might be related to internal waves. It might be the storm breathing. It might be a signal from the deep interior, a message from the metallic hydrogen ocean below. The storm is talking to us. We just have not learned how to listen yet, but we are trying. That is the point. July 11th, 2017 was the day we stopped looking at the storm and started listening. It was the day we realized that the Great Red Spot is not a feature. It is a phenomenon. It is a process. It is a living, breathing, self-sustaining engine of chaos and order. And it has been doing this for longer than humanity has existed. We are the newcomers. We are the ones who just arrived, blinking in the light, trying to make sense of a world that has been turning long before we had eyes to see it. Juno gave us those eyes, and what they saw will take a generation to understand. But here's where it gets really strange. We've been looking at that red spot for centuries, painting it, photographing it, wondering what gives it that angry, bloodshot eye look. And for the longest time, we just assumed the colour was tied to the storm itself. Like, the deeper you go, the redder it gets. Makes sense, right? But Juno, in its quiet, methodical way, flipped that assumption on its head. It turns out the red is only skin deep. Literally. The iconic colour, that deep rusty orange we've all come to recognise, extends maybe a few dozen kilometres down. That's it. Below that, the storm is just white, ammonia ice. A massive churning blizzard wrapped in a thin painted shell. Think about that. The Great Red Spot is essentially a white hurricane wearing a red hat, and that hat is only a few miles thick on a storm that's thousands of kilometres wide. It's like painting a single stripe on a freight train and calling the whole thing colourful. So what is that red pigment? Scientists call it a chromophore. which is just a fancy word for a molecule that absorbs certain wavelengths of light and reflects others, giving it colour. But here's the thing, for decades we had no idea what the chromophore actually was. We had theories, we had lab experiments, we had graduate students spending sleepless nights trying to recreate Jupiter in a test tube, but Juno gave us the context we were missing. It showed us that this colour is not a stable, permanent feature. It is transient. It is constantly being created and destroyed, like a chemical sunburn that never quite heals. The ultraviolet radiation from the sun is relentlessly pounding the top of Jupiter's atmosphere, breaking apart molecules of ammonia and acetylene, and when those molecules get shredded, they recombine into something new, something coloured, something that looks like a thin, organic gunk. And here's the kicker. That gunk doesn't last forever. It gets bleached, broken down, or buried by new material. The storm has to continuously feed freshened ingredients into the photochemical reactor just to keep its colour. It's like a campfire that only stays lit if you keep throwing logs on it. But where are those logs coming from? Juno's data suggests the storm's extreme updrafts are the key. The Great Red Spot is not just spinning, it is vertical. It is pulling material up from deep within Jupiter's atmosphere, from layers where the pressure is 100 times what we feel on Earth. Down there, in the hot, dark depths, complex organic chemistry is happening. Simple molecules are being cooked into longer chains, creating compounds that are unstable at the surface but survive the rapid ascent. Think of it like a deep-sea hydrothermal vent on Earth, where bizarre life thrives on chemicals. Except on Jupiter, the life is chemical, and when that deep material gets shot up into the sunlight, the UV radiation hits it and creates the red colour. But it's a narrow window. If the updraft is too strong, the material gets blasted too high, gets overexposed and turns pale. If the updraft is weak, the material doesn't reach the photochemical zone at all. The Great Red Spot is balancing on a knife's edge of pressure, temperature and radiation. And that balance is delicate, which brings us to the colour change. If you look at paintings of Jupiter from the 1800s, that spot was brick red, deep, dark, almost bloody. Today it's more of a pale salmon, sometimes almost white. What happened? Did the storm get tired? Did it run out of ink? No, it got smaller. For over 100 years, the Great Red Spot has been shrinking. In the 1800s, it was wide enough to swallow 3 Earths. Now, it can barely fit one. As the storm contracts, the dynamics change. The updrafts get less intense. The material gets less time to cook. The chromophore becomes thinner, less concentrated. It's like a pot of stew that's been boiling for centuries, but someone keeps turning the heat down. The flavour is still there, but it's getting watered down. And there's another factor, ammonia. We now know the storm's ammonia levels are not constant. They vary, both vertically and temporally. When the ammonia concentration dips, the production of the chromophore drops. The storm gets paler. When ammonia spikes, maybe from a deep convective event, the colour temporarily deepens. The Great Red Spot is not a static painting. It's a living, breathing, photochemical reactor with a fluctuating fuel supply. In 2014, a group of researchers finally did what no one had done before. They recreated the Great Red Spot in the lab. Not the whole storm, obviously, but they built a chamber that mimicked the temperature, pressure, and chemical composition of Jupiter's upper atmosphere. They pumped in ammonia and acetylene gas, then blasted them with ultraviolet light. And what did they see? The gas turned red. Specifically, it turned the exact shade of orange that matches Juno's observations. This was the smoking gun. The experiment proved that the red colour is not some exotic, unknown molecule. It's a mixture of simple organic compounds, tholins, as astrochemists call them. These are the same kinds of gunk that create the reddish haze on Saturn's moon Titan and on Pluto. It's a universal process. When you have methane or ammonia and you add UV light, you get complex organic molecules. Jupiter's Great Red Spot is just a very large, very violent version of the same chemistry that happens on distant, frozen moons. And that leads us to the most mind-bending implication of all: exoplanets. Think about it. We now know that a storm on Jupiter, a planet in our own backyard, is actively creating complex organic molecules using nothing but sunlight and simple gases. What does that mean for the thousands of hot Jupiters we've discovered? These are gas giants orbiting perilously close to their stars, baked in ferocious UV radiation, with temperatures that melt lead and winds that scream at supersonic speeds. If our own Jupiter's storm can create organic compounds under relatively mild conditions, what are those hellish worlds cooking up? Imagine a hot Jupiter with a permanent planet-sized storm on its day side, constantly blasted by stellar UV. That storm could be churning out organic molecules on an astronomical scale. Tholins, amino acids, the building blocks of life. Not life itself, but the raw ingredients that, on Earth, eventually led to it. We are not just looking at a weather phenomenon. We are looking at a planetary-scale prebiotic chemistry factory. Every time we see a red or orange glow on a distant exoplanet, we should wonder, is that a photochemical haze? Is that a storm making its own colour? Is that in some small way a reflection of the same processes that made our own world habitable? The great red spot, for all its fury and majesty, might be telling us something profound. It might be evidence that organic chemistry is not rare. It might be common. It might be inevitable, as long as you have a star, a thick atmosphere, and a few simple gases. Jupiter is not an exception. It might be the rule, and that changes everything. We look up at that red eye, and we see a blemish. But maybe it's a mirror. Maybe it's showing us how the universe, in its cold and violent way, cooks up the ingredients for life. The colour is not just a cosmetic detail. It is a chemical signature. It is a whisper from the depths of a storm that has been boiling for centuries, telling us that the line between weather and chemistry is thinner than we ever imagined. And on those far-off worlds, where the winds never stop and the light never fades, those whispers might be screams. The great red spot is our teacher. It teaches us that a storm is not just a storm. It is a laboratory, and the universe is full of them, and that laboratory is not idle. The great red spot has been running continuous experiments for centuries, and we are only now beginning to read the results. The chemical factory model forces us to reconsider what we mean by weather on a gas giant. We typically think of clouds, wind, and rain, but on Jupiter the weather is inextricably linked to photochemistry. The storm is not just a wind pattern, it is a chemical engine. The same updrafts that create the towering cloud decks also transport the raw materials for organic synthesis. The same ultraviolet light that bleaches the colour also drives the reactions that create it. The entire system is a feedback loop of destruction and creation, a self-sustaining cycle that has been running for centuries, if not millennia. Consider the vertical structure of the storm. Juno's microwave radiometer, which can peer deep beneath the cloud tops, revealed that the great red spot extends hundreds of kilometres downward, far deeper than the neighbouring bands. The storm is rooted in the deep atmosphere, drawing energy from Jupiter's internal heat. At those depths, the temperature is hot, the pressure is crushing, and the chemistry is wild. Simple molecules like methane and ammonia are broken apart by the heat and pressure, then reassembled into more complex chains. These are the precursors to the chromophore. When they are lofted upward by the storm's powerful convection, they are exposed to the full fury of the sun. The ultraviolet light acts like a chemical catalyst, rearranging the molecular bonds to create the distinctive red shade. But here is the subtlety. The reaction is not instantaneous. It takes time. The longer the material lingers in the ultraviolet zone, the redder it becomes. This is why the edges of the storm are often a different shade than the centre. The edges are turbulent, mixing in fresh, unreacted material from the surrounding bands. The centre is a slow, steady updraft that allows the chemical reaction to mature. The result is a gradient of colour, from pale orange at the periphery to deep brick red in the core, provided the storm is active enough to sustain the vertical transport. This gradient was far more pronounced in the past. Historical observations, dating back to the 17th century, describe the spot as a permanent spot with a reddish hue. But the descriptions vary wildly. Some early astronomers saw it as a deep crimson. Others called it a rose-coloured oval. Still others saw it as a faint, almost invisible blemish. This variability is not just a matter of differing telescopes or observational skill. It is a real physical change in the storm's chemical output. The Great Red Spot has phases. It has moods. It brightens and darkens over decades, sometimes cycling through periods of intense colour and near invisibility. In the 1920s, for example, the spot was described as pale pink, barely distinguishable from the surrounding cloud bands. By the 1960s, it had deepened to a rich salmon. In the 1970s, the Voyager spacecraft captured it as a vivid orange-red. Today, it is fading again, closer to a pale peach than a stormy red. What drives these fluctuations? The leading theory points to a process called ammonia injection. The storm periodically receives a surge of ammonia from the deep atmosphere, perhaps triggered by a massive convective event, or a change in the storm's internal dynamics. This ammonia spike provides fresh fuel for the photochemical reactor, temporarily deepening the colour. Between these surges, the existing chromophore gets bleached by the relentless UV, and the storm slowly fades. The Great Red Spot is not a steady flame. It is a flickering candle, flaring and dimming over the centuries. But there is another, more unsettling possibility. The colour change could be a symptom of the storm's declining health. The Great Red Spot is shrinking. This is an established fact. It has been observed shrinking for over a century, accelerating in recent decades. In the late 1800s, the spot was estimated to be about 40,000 kilometres wide. By the time Voyager flew past in 1979, it had shrunk to around 25,000 kilometres. Hubble images from the 1990s showed it at about 20,000 kilometres. By 2014, it had dropped to roughly 16,000 kilometres. Today, it is barely 14,000 kilometres wide. That is a reduction of over 60% in a little more than a century. If the trend continues, the Great Red Spot could become a Great Red Circle, or even a Great Red Memory within another 100 years. But size is not the only thing changing. The wind speeds are shifting. The outer winds, the ones that create the characteristic counterclockwise spin, have actually increased in velocity, reaching over 400 miles per hour. But the inner core, the calm eye of the storm, appears to be becoming less organized. The storm is stretching out, like an old rubber band losing its elasticity. Some models suggest the storm is interacting with smaller eddies and vortices, being cannibalized by the surrounding turbulence. Other models point to a long-term shift in Jupiter's climate, perhaps tied to the planet's internal heat balance. And with this shrinking comes a change in the storm's vertical structure. As the storm compresses horizontally, it may also be thinning vertically. The powerful updrafts that once dredged material from hundreds of kilometers deep may be weakening. The conveyor belt that feeds the chromophore factory is slowing down. Less deep material reaches the ultraviolet zone. The chemical reactor starves. The colour fades. The Great Red Spot is not just getting smaller, it is getting shallower. Juno's gravity measurements, which can map the depth of atmospheric features, have shown that the storm's roots are becoming less pronounced. The deep, massive structure that once anchored the storm in Jupiter's interior is eroding. The storm is becoming a surface feature, a thin skin of wind and colour, detached from the planetary engine that sustained it for centuries. This is a profound change. The Great Red Spot has been a permanent fixture of Jupiter's appearance for as long as we have had telescopes. The idea that it might be dying, that it might one day merge into the surrounding bands and disappear, is both sad and scientifically transformative. It forces us to ask, what replaces it? Jupiter is a dynamic planet. It will not be empty. New storms will form, perhaps smaller, perhaps larger. The planet's internal heat will always create weather. But will we ever see another storm of such longevity and character? The Great Red Spot is a living fossil, a weather pattern that has survived for centuries. Its passing, if it passes, will be the end of an era. This brings us full circle to the colour itself. The colour is not just a chemical curiosity. It is a biography. Every shade of red, every subtle shift in hue is a chronicle of the storm's history. The deep reds of the past speak of a time when the storm was vast and powerful. when the updrafts were vigorous and the ammonia supply was rich. The pale orange of today tells a story of decline, of a starved reactor and a thinning atmosphere. The colour is the storm's autobiography, written in the language of organic chemistry, and because we have been watching for so long, we can read that autobiography. We can see the chapters of strength and the chapters of weakness. We can observe the storm's response to external forces, like the impact of Comet Shoemaker-Levy 9 in 1994, which briefly darkened the storm and altered its appearance. We can track its interaction with smaller storms, the way it absorbs them and sometimes ejects them. The Great Red Spot is not a simple object. It is a complex, evolving system, and its colour is the most accessible indicator of its internal state. So when you look at an image of Jupiter and see that red spot, do not just see a storm. See a chemical factory that has been running for centuries. See a photochemical reactor that is powered by the sun and fueled by the planet's deep interior. See a historical document that is constantly being rewritten. See a dying giant whose colour is fading as its strength wanes. And then think about the wider implications. If this process is happening on Jupiter, it is happening elsewhere. It is happening on Saturn, where similar photochemical reactions create a yellowish haze. It is happening on Titan, where the atmosphere is thick with organic molecules. It is happening on Pluto, where the reddish colour of its surface is produced by the same kind of tholins, and it is happening on countless exoplanets in systems far from our own. The Great Red Spot is a local example of a universal process. It is a reminder that the universe is constantly cooking organic molecules, that the line between geology, meteorology and biochemistry is blurry, and it is a warning that even the most permanent-looking features are temporary. The Great Red Spot is not eternal, nothing is. But while it lasts, it teaches us something profound about the way worlds work, and about the thin chemical thread that connects a storm on Jupiter to the potential for life in the cosmos. That red colour, that iconic blemish, is a message, and we are only just beginning to decode it. And so we come to the heart of the mystery, the part of the story that feels almost like watching a living thing fade. We have marvelled at the storm's colour, woven theories about its chemistry, and wondered if its clouds might ferry the building blocks for life. But there is a cold, hard truth lurking beneath that beauty, a truth that astronomers have been tracking for over 140 years. The Great Red Spot is shrinking, and not just a little. It is vanishing before our eyes. When we talk about the spot in the context of the grand sweep of Jovian history, we are talking about a patient on life support, a giant that is slowly, inexorably, losing its grip on existence. But as with any good tragedy, the details are what make it heartbreaking. Let us go back to the beginning of our records. The year is 1879. Telescopes were crude. Photography was in its infancy, but astronomers were keen observers. They measured the Great Red Spot and recorded its diameter at an astonishing 41,000 kilometres. Let that number sink in for a moment. 41,000 kilometres. That is wider than the entire planet Earth. You could drop our world into that storm and it would roll around like a marble in a bathtub. It was a colossal, sprawling vortex, a wound on Jupiter that seemed permanent, eternal. Fast forward to the dawn of the space age, to the Voyager flybys of 1979. The spot had already shrunk. It measured roughly 23,000 kilometres across. Still enormous, still dwarfing our planet, but already a shadow of its 19th century self. The shrinkage had begun long before we had satellites to witness it, and it has not stopped since. By the time the Hubble Space Telescope began its long vigil in the 1990s, the trend was undeniable. The numbers became a kind of slow-motion horror show for planetary scientists. Year after year the spot got smaller. The raw data is stark. In 1879, 41,000 kilometres. By the late 20th century, roughly 23,000. By the early 2000s, it was down to around 20,000. And then the pace quickened. The period between 2012 and 2014 became known as the alarming years. The storm began losing diameter at a rate of almost 1,000 kilometres per year. 1,000 kilometres. That is roughly the distance from London to Paris. Every single year, the storm was giving up a chunk of itself the size of a European country. Imagine standing on a beach, watching the tide pull a metre of sand out to sea every minute, and knowing there is nothing you can do to stop it. That is what the scientists felt as they watched the data pour in from Hubble and from ground-based observatories. The storm was not just shrinking, it was collapsing. But here is where the story gets weird. As the storm got smaller, its geometry began to change. For most of its recorded history, the Great Red Spot was a distinct oval, stretched out horizontally like a giant angry eye that had been pressed flat. But as it contracted, that oval began to round out. It started to look less like a stretched out pancake, and more like a circle, a perfect, almost geometric circle. The change in shape told them something fundamental about the storm's internal dynamics. A stretched oval is an unstable shape for a long-lived vortex. It is prone to shearing and tearing. As the storm lost mass, it became more compact, more stable in shape, but paradoxically, more vulnerable in the long run. In 2015, a team of researchers led by a scientist named Glenn Orton at NASA's Jet Propulsion Laboratory dropped a bombshell. Based on the current rate of shrinkage, they predicted that the Great Red Spot could completely disappear within 20 years. 20 years. That is not geological time. That is not even the lifespan of a single human generation. It is the time it takes for a child to grow up and become an adult. The prediction sent shockwaves through the planetary science community. Suddenly, the Great Red Spot was not just a planetary feature. It was a ticking clock. The debate that followed was fierce. Some scientists argued that the prediction was too pessimistic, that the storm has lasted for centuries, maybe longer, and that it might be undergoing a natural fluctuation. They pointed to historical records that suggested the spot had changed size before, sometimes growing, sometimes shrinking. Others countered that the modern data was irrefutable. The rate of shrinkage was accelerating. The storm was in a death spiral, and no amount of wishful thinking would save it. The Hubble Space Telescope, with its continuous photographic record dating back to 1995, became the key witness in this debate. Hubble's images are not just pretty pictures. They are a time-lapse film of a dying giant. When you look at them in sequence, year after year, you do not just see a shrinking spot, you see internal changes. The core of the storm, the deepest red, began to fade. The surrounding bands of cloud started to encroach, like desert sand creeping into a shrinking oasis. The structure became less defined, more chaotic. It was like watching a great painting slowly being erased, stroke by stroke. And then, in 2019, something truly bizarre happened. Amateur astronomers around the world, the backyard observers who spend their nights hunched over telescopes in cold, dark fields, noticed something strange. A flake. A piece of reddish material was breaking off the southern edge of the Great Red Spot. It was not a large piece, maybe a few 100 kilometers across, but it was clearly detaching from the main body. This flake drifted away, lasting for about 10 days before dissipating into the surrounding clouds. It was visible through moderate-sized amateur telescopes, and the images flooded online forums. The flake event of 2019 became a sensation. It was physical proof that the storm was not just shrinking, but actively disintegrating. The material was being sheared off, pulled away by the powerful jet streams that surround the spot. It was a slow-motion death by 1,000 cuts. But the flake was just a symptom. The real cause of the shrinkage is far more insidious, and it lies in the way the storm interacts with its environment. For years, scientists believed that the Great Red Spot fed on smaller storms, the swirling anticyclones that pop up all over Jupiter's surface. They thought these smaller vortices were like snacks, little bits of energy that the big spot could absorb to sustain itself. It made sense. A big predator eats smaller prey. But recent observations have turned that idea on its head. We now know that when small storms get absorbed by the Great Red Spot, they do not strengthen it, they disrupt it. They act like sand thrown into a finely tuned engine. The small anticyclones, which spin in the same direction as the Great Red Spot, bring with them different temperatures, different wind speeds, and different chemical compositions. When they merge with the main spot, they create turbulence at the edges, vorticity, that actually erodes the storm's structure instead of feeding it. It is a paradox. The very mechanism that was supposed to keep the storm alive is in fact helping to kill it. Every time the Great Red Spot devours a smaller rival, it takes a wound, and that wound cannot fully heal. This brings us to the next twist in the story. As the storm shrinks, its wind speeds increase. This sounds counterintuitive. You would expect a dying storm to grow weaker, to slow down, to become lethargic. But the opposite is happening. The energy of the storm, the raw kinetic force, is concentrating into a smaller area. It is like a spinning figure skater pulling their arms in. As the radius decreases, the rotation rate increases. The winds at the outer edge of the Great Red Spot, which were once measured at around 300 miles per hour, have actually accelerated. They are now pushing up to 400 miles per hour, maybe even higher in some localized areas. The storm is not fading away quietly. It is burning brighter, spinning faster in its final act. It is a beautiful and terrifying thought. A giant that is consuming itself from within. The energy that once sustained a vast oval is now being squeezed into a tight, compact circle. The internal pressure is building. Some researchers have even suggested that the shrinking might actually make the storm more intense for a time, before it finally collapses. It could become a kind of super vortex, small but incredibly powerful, and then just vanish. But hold on, in 2023 a new study came out that threw another wrench into the narrative. By analysing the most recent Hubble data, scientists found that the rate of shrinkage appears to have slowed down. Since about 2020, the storm has been losing diameter at a much slower pace. It is still shrinking, make no mistake about that. But the breakneck speed of the 2012 to 2014 period seems to have eased. The storm may be approaching an equilibrium, a state where its internal dynamics are balanced enough to resist further rapid erosion. This does not mean the storm is saved. It could simply mean that the storm has found a temporary stable configuration, a smaller, rounder shape, that is less vulnerable to the shearing forces of the surrounding jet streams. It might hover at this new size for decades, like an old wound that has scarred over before something else triggers another collapse. But it could also mean that the 20-year prediction was too alarmist. It is possible that the Great Red Spot will persist in some form for another century. We simply do not know. And that is the maddening, beautiful truth about this storm. It is a living laboratory of chaos. It does not follow our timetables or our predictions. It follows its own logic, a logic written in the physics of a massive gas giant that we are only beginning to understand. So as we stand here in the 2020s, watching the Great Red Spot through the lenses of Hubble and the James Webb Space Telescope, we are witnessing something that no human has ever seen before. We are watching the final chapters of a story that began before the Roman Empire. The storm is changing. It is retreating. It is concentrating its power. It is sending us signals in the form of red flakes and accelerating winds, and we are left to interpret them. The history of the Great Red Spot is not just a history of atmospheric science. It is a history of human observation, of our desire to track, measure, and understand something that is inherently untamable. It is a reminder that even the most iconic features of our solar system are not permanent. They are ephemeral. They rise, they rage, and they fade. The cosmos does not care about our sentimental attachment to a red spot. It cares only about the relentless laws of fluid dynamics, of energy transfer, of entropy. And as the spot shrinks, it is teaching us a final, painful lesson. Nothing lasts forever, not on Jupiter, not anywhere. But while it lasts, while that crimson eye still stares down at us from 1 billion kilometers away, it remains the most magnificent storm in the solar system, a testament to the power of nature, and a humbling reminder that we are just lucky enough to have been born at the right time to see it before it goes. But here is where the story gets truly bizarre. For decades, we thought we understood this thing. We thought the Great Red Spot was a single coherent hurricane, just scaled up to planetary proportions. We were wrong. It took NASA's Juno spacecraft, diving closer to Jupiter than any machine before it, to reveal the truth. The storm is not one thing, it is many things. It is a chaos of layers, a tempest that contradicts itself at every depth. This is the interior physics of the Great Red Spot, the storm within the storm. Juno carries an instrument called the microwave radiometer, a marvel of engineering. It peers through the thick clouds of Jupiter, seeing deeper than any camera ever could. When it turned its gaze on the Great Red Spot, it found something that made scientists scratch their heads. The storm does not behave like a single solid object. Layers of ammonia gas move at different speeds, often in completely different directions. Imagine a skyscraper where every floor is spinning in its own independent hurricane, and you start to get the picture. The top of the storm, the part we see from Earth, rotates counterclockwise. But drop down just a few dozen kilometers, and the gas might be moving sideways, or even backwards, relative to the surface. It is a tangled mess of currents, a storm within a storm within a storm. It is not one eye, it is a system of eyes stacked on top of each other, each with its own personality. And then there is the heat. At roughly 50 kilometers below the cloud tops, Juno detected something remarkable, anomalously warm gas rising in massive convective plumes. These are not gentle updrafts. These are violent, churning columns of heat, punching upward through the cooler atmosphere. This is the engine room. This is where the storm gets its power. Think of it like a pot of boiling water. The heat comes from below, creating bubbles that rise and burst at the surface. The Great Red Spot is exactly the same, except the pot is the size of Earth. And the bubbles are storms that could swallow continents. The energy budget here is almost incomprehensible. We are not talking about a few lightning strikes. We are talking about millions of atomic bombs worth of energy every hour. That is not a typo. That is the raw, staggering power required to keep this crimson eye open. But where does that energy actually come from? It does not come from the sun. Jupiter is so far out that sunlight is weak, barely a fraction of what we get on Earth. The energy source is internal. It is a ghost from the past, from the very birth of the solar system. Jupiter is still slowly contracting, still cooling down from the catastrophic heat of its formation 4.5 billion years ago. As the planet shrinks, it releases gravitational energy, a slow, steady, relentless squeeze that generates heat from within. That heat rises, fueling the convection, feeding the storm. The Great Red Spot is essentially a scar on the surface of a world still settling into itself. It is a living relic of the ancient chaos that created the planets. But here is the interdependency that truly surprises scientists. The Great Red Spot does not exist in a vacuum. It is flanked by massive jet streams, rivers of gas that wrap around the entire planet, flowing east and west at hundreds of miles per hour. For a long time, we assumed these jet streams were just a passive backdrop, a weather feature the storm happened to sit in. The computer simulations say otherwise. They show a codependence, a symbiotic relationship, almost biological in its intimacy. When scientists run simulations that remove those jet streams, the Great Red Spot does not just weaken, it dies. Within 50 simulated years, the storm dissipates completely. It loses its shape, its spin, its identity. It fades away into the general atmospheric noise. The jet streams and the storm are locked together. The storm draws energy from the shear of the jets, while the jets themselves are shaped and maintained by the presence of the storm. They need each other. It is not a transient feature. It is a stable structure, a permanent fixture of the planet's global circulation. The Great Red Spot is not a visitor. It is a resident, a landlord that has negotiated a long-term lease with the atmosphere itself. And then there is the gravity. Juno measures the gravitational field of Jupiter with exquisite precision, mapping subtle variations in the pull of the planet. When the data came back for the Great Red Spot, it contradicted every earlier model. The mass of the storm is concentrated in the upper layers, near the cloud tops. The deep roots, the parts that stretch down into the planet, are actually lower density. This is the opposite of what we expected. We thought the storm would be a column of dense gas, extending deep into the interior like a solid pillar. It is not. It is top-heavy. It is a shallow, high-density cap sitting on top of a much lighter, diffuse base. This changes everything about how we model Jovian storms. It means the energy is being dumped into the upper atmosphere, not channeled downward. It means the storm is more like a blister on the skin of the planet than a root system extending into the mantle. The physics is strange, and it is beautiful, so let us put it all together. The Great Red Spot is a layered chaotic system of ammonia currents moving at different speeds, powered by rising plumes of hot gas from a planet, still squeezing itself from the inside out. It burns through the energy of millions of atomic bombs every hour. It is held in place by jet streams that would tear a lesser storm apart, and it repays the favour by anchoring those same jet streams in a dance of mutual dependence. And it is shallow, top-heavy, a thin crust of fury sitting on a deep, quiet foundation. This is not the storm we thought we knew. This is something far stranger, far more complex, and far more humbling. It is a window into the soul of Jupiter itself, a planet that refuses to give up its secrets easily, and as we peer deeper, we begin to realize something profound. The Great Red Spot is not just a weather event. It is a living system, a self-sustaining engine that has outlasted empires and ice ages and the entire written history of humanity. It is a creature of pure physics, a beast born from the contraction of a gas giant, fed by the heat of its own slow collapse, and tamed by the very winds that should destroy it. The storm within the storm is not just a curiosity, it is a lesson. It tells us that nature finds stability in chaos, that order emerges from turbulence, and that the most violent forces in the universe can settle into a rhythm that lasts for centuries. We just have to be humble enough to listen. And Juno is listening, still diving through that radioactive hellscape, sending back whispers of data from the deep. The story is far from over. The most interesting part is just beginning, and so Juno continues to dive, braving the most intense radiation environment in the solar system, a cauldron of charged particles trapped by Jupiter's immense magnetic field. The spacecraft's electronics are housed in a titanium vault, a fortress designed to withstand the equivalent of 1 million dental X-rays per orbit. Every time Juno swoops low over the Great Red Spot, it is a gamble. But the risk is worth it, because the secrets we are uncovering rewrite the textbooks in real time. The historical context of our understanding is itself a story of slow, painful revelation. When Giovanni Cassini first observed the spot in 1665, using a primitive telescope from his observatory in Bologna, he described it as a permanent spot. He had no idea what it was. He thought it might be a surface feature, perhaps a mountain or a continent on the solid surface of Jupiter. For 2 centuries, astronomers debated its nature. Some thought it was a shadow. Others believed it was a flaw in the lens, an optical illusion. It was not until the 19th century, with better telescopes, that the swirling nature of the spot became apparent, and the word storm was first whispered in the halls of the Royal Astronomical Society. But even then the scale was misunderstood. We thought it was a surface phenomenon, a patch of weather on a planet that was mostly atmosphere. We did not grasp that the spot is thicker than the entire atmosphere of Earth, a vertical column of fury punching through multiple layers of Jovian sky. The voyage of flybys in 1979 changed everything. For the first time, we saw the spot up close. The images were grainy, pixelated by modern standards, but they were revelatory. We saw the intricate cloud bands, the counter-rotating eddies, the pale orange tendrils wrapping around the centre. We saw that the spot was not static, but alive, pulsing, changing shape from year to year. And we saw something else that puzzled the mission planners. The spot appeared to be interacting with smaller storms, swallowing them whole, absorbing their energy. The Great Red Spot is a predator. It consumes smaller vortices, stealing their kinetic energy to sustain its own rotation. This cannibalism is part of its survival strategy. It does not just sit there, placid and eternal. It hunts, it feeds, it grows and shrinks in cycles that span decades, responding to the availability of smaller storms in its vicinity. The spot is not a museum piece. It is an active, hungry organism, and its appetite is voracious. But the shrinking is real, and it is accelerating. Historical records from the 19th century show that the spot was once large enough to contain 3 Earths side by side. By the time Voyager arrived, it had shrunk to 2 Earths. By the time the Hubble Space Telescope began monitoring it in the 1990s, it was down to 1.5. Today, as of the latest measurements, the Great Red Spot is barely 1.3 Earths wide. It is still enormous by any human standard, but the trend is unmistakable. Something is changing. The leading theory is that the jet streams have shifted slightly, reducing the shear that feeds the storm. Another hypothesis involves a change in the internal heat flux of Jupiter itself. Perhaps the planet is cooling faster than expected, or perhaps the convection cycles in the deeper atmosphere are reorganizing. We do not know. The data is still too sparse, but the implication is chilling. The Great Red Spot may be dying, not in geological time, but in human time. Within our lifetimes, or within the lifetimes of our children, the storm could collapse into a smaller, weaker vortex, or even dissipate entirely. A feature visible to human eyes since the time of Newton and Leibniz may simply vanish, leaving only a pale scar in the Jovian clouds. And yet, even as it shrinks, the storm is changing in other ways. The colour is deepening. In recent decades, the Great Red Spot has become a deeper, richer red, almost blood-coloured, compared to the faded salmon pink of the Voyager era. This is not just an aesthetic shift. It tells us something about the chemistry of the storm. The red colour is thought to come from complex organic compounds, created when ultraviolet radiation from the sun interacts with the ammonia and acetylene in the upper atmosphere. As the storm shrinks, the concentration of these compounds may be increasing, leading to a more intense hue. Or perhaps the storm is simply churning up different materials from deeper layers, exposing fresh chemical compounds to sunlight. The colour is a chemical fingerprint, and it is changing in real time. The deepest structure, however, remains the greatest mystery. The microwave radiometer data from Juno suggests that the storm has a root system, but it is not a solid column of dense gas. Instead, it is a diffuse tangled network of convection cells, extending perhaps hundreds of kilometres into the atmosphere, but not all the way to the hypothesized water cloud layer, which lies roughly 500 kilometres below the visible cloud tops. This is the key to the storm's longevity. If the roots were deeper, the storm would be more stable, more resistant to change. But if the roots are shallow, the storm is vulnerable. It is a delicate balance, a tightrope walk between destruction and persistence. The Great Red Spot is not a fortress. It is a high-wire act, and the winds of Jupiter are always threatening to push it off balance. And perhaps that is the most profound lesson of all. The universe is not a place of static perfection. It is a place of dynamic equilibrium, of systems that persist only as long as the forces that sustain them remain in balance. The Great Red Spot is a reminder that even the most seemingly eternal features of the cosmos are temporary. Mountains erode, stars burn out, oceans dry up, and even the largest, most violent storm in the solar system can fade away, leaving no trace but a memory in the databanks of human instruments. We are fortunate to live in the age of Juno, to witness this drama as it unfolds. We are the first generation to truly see the storm within the storm, to understand that the Great Red Spot is not a single entity, but a symphony of chaos, a layered, interdependent, hungry, dying, and yet still magnificent wonder of the cosmos. And as Juno continues its orbits, diving ever closer to the cloud tops, we wait for the next revelation, the next surprise, the next piece of data that will force us to rethink everything we thought we knew. The story of the Great Red Spot is still being written, and we are the ones holding the pen. But beneath the beautiful chaos of that swirling, rust-coloured storm, beneath the churning ammonia ice and the howling winds, there is something else. Something that crackles, something that flashes, something that turns the Great Red Spot from a mere weather phenomenon into a genuine electrical engine. And if you thought the winds were violent, wait until you see what happens when the sky starts throwing bolts of lightning that make our own thunderstorms look like a flickering light bulb in comparison. Let's rewind the clock a little. Way back in 1979, a spacecraft called Voyager 1 was speeding through the outer solar system, sending back the first close-up postcards of the giant planets. And when its cameras pointed at Jupiter, they saw something nobody quite expected. Lightning, not the soft, distant flashes we get on a summer night, but enormous, brilliant pulses of light ripping through the Jovian atmosphere. This was a huge discovery. But here's the thing that really puzzled the scientists back then. The lightning wasn't happening where you might expect it. On Earth, our thunderstorms tend to cluster around the equator, where the sun heats the ground and stirs up all that moisture. On Jupiter, the lightning was almost entirely concentrated near the poles. The equator, including the region of the Great Red Spot, seemed oddly quiet. It was a mystery that would sit in the back of planetary scientists' minds for decades, just waiting for the right mission to come along and crack it open. That right mission turned out to be Juno. When Juno arrived at Jupiter in 2016, it brought with it an instrument called the Microwave Radiometer, or MWR for short. And the MWR had a very specific superpower. It could see through the thick clouds. It could peer down into the deeper layers of the atmosphere, listening not for visible light, but for radio waves. And that made all the difference. Because lightning, it turns out, doesn't just make a flash you can see with your eyes. It also generates a burst of radio static, a specific frequency signature that cuts through the clouds like a knife through butter. And when the Juno team looked at the data from the MWR, they got the shock of their careers. There they were, the unmistakable radio signals of lightning. But not just anywhere. The signals were coming from directly inside the Great Red Spot, and they were flooding out of the storm at a rate that made the polar lightning look positively shy. So what exactly are we talking about here? Let's get technical for a second, but I promise I'll keep it interesting. The brightness of this electrical activity spanned a massive range of frequencies, from about 600 MHz all the way down to 150 kHz. Now, that range is actually very familiar to us. It's exactly the same kind of radio static that our own lightning produces on Earth. It sounds the same, crackles the same, behaves the same, but the scale is where things get ridiculous. The Jovian lightning was not just a little bit more powerful than ours. It was orders of magnitude more powerful. We're talking about bolts that pack the energy of a small nuclear weapon, but happening inside a gas giant, miles and miles below the visible surface, inside the guts of a storm that could swallow our entire planet whole. And here is where the detective work really kicks in. By analysing the radio signals, the Juno scientists could pinpoint exactly where this lightning was originating. They weren't just random flashes near the cloud tops. They were happening deep, really deep. The source was located somewhere between 50 and 65 kilometers below the ammonia cloud tops that we see in those famous images. That depth is critical, because that layer of the atmosphere is the water cloud layer. It's where the temperatures are just right for water to exist, not as vapor, not as ice, but as actual liquid droplets. And you need liquid water to make lightning. Let me explain that physics, because it's beautiful in its simplicity. Inside a thundercloud, whether it's on Earth or Jupiter, you have collisions. Tiny ice crystals and larger water droplets smash into each other at high speed. When they rub together, they exchange electrical charge. The lighter ice particles become positively charged and get swept upward by the updraft, while the heavier water droplets become negatively charged and sink. Eventually, the difference in charge becomes so enormous that the air itself can't hold it anymore. The electricity has to go somewhere, and that release is what we call lightning. So the fact that Juno found lightning inside the Great Red Spot tells us one very simple, very powerful thing. There is liquid water in that storm, and not just a little bit. The amount of electrical activity suggests a significant active water cycle churning away in the deep Jovian atmosphere. This is a huge deal, and it leads us to one of the biggest unanswered questions in all of planetary science. Just how much water does Jupiter actually have? You see, Jupiter's water abundance is not just a trivia question. It's a critical constraint, a fossil record of how our entire solar system formed. Here's why. The leading theories suggest that Jupiter formed either relatively close to the Sun, where it was warm and water was scarce, or much farther out, in the cold outer regions of the early solar system, where water ice was abundant. If Jupiter formed out in the cold, you would expect it to be heavily enriched in water compared to the Sun's composition. If it formed closer in, you would expect it to be water poor. For decades, we couldn't get a clear answer. Previous probes, like the Galileo mission, sent a descent probe into Jupiter's atmosphere back in the 1990s, and it returned some very confusing data. It found a lot less water than models predicted. But that probe entered a particularly dry hotspot. It was like dropping a bucket into the Sahara Desert and concluding that the entire Earth is a desert. It wasn't representative of the whole planet. Juno's lightning data is changing that story entirely. By proving that lightning is widespread and powerful inside the Great Red Spot and other storm systems, Juno is giving us a much better picture. The lightning is telling us that the deep atmosphere is significantly more water-enriched than those old Galileo readings suggested. The radio static from those deep Jovian storms is singing a new song, and the implications are nothing short of earth-shaking. If Jupiter is indeed full of water, if it truly is a water-rich planet, then that strongly supports the idea that it formed in the cold outer reaches of the solar system, before migrating inward to its current position. It changes our understanding of how giant planets are born, how they move, and how they shape the architecture of everything around them. It even affects how we think about the delivery of water to the inner planets, including our own Earth. So the next time you look up at the night sky and see Jupiter shining bright, remember this. It's not just a painted orb of gas. It's a living, breathing, electrically active world. Inside that silent-looking red spot, there is a storm factory churning out some of the most powerful lightning in the solar system. And every single one of those flashes is a little beacon, a tiny burst of radio static that tells us about the deep, hidden layers of a world that still refuses to give up all its secrets. The Great Red Spot is not just a storm. It is an electrical engine, and Juno has just discovered how to listen to it. And that engine is telling us the forgotten story of where Jupiter came from, and by extension, where we came from too. And so, in the wake of Juno's thunderous revelations about Jupiter's hidden electrical heart, we have to ask ourselves a question that should send a shiver down the spine of anyone who's ever looked up at the night sky. How did we get here? How did we go from knowing this storm was just a big red smudge to understanding it's a living, breathing engine that might hold the keys to our own creation? The answer, as with so many great discoveries, begins with a pair of robotic pioneers that took a wild gamble and decided to point their cameras at a monster. The year was 1979. The Cold War was still simmering, disco was dying a slow death, and NASA was about to pull off one of the greatest heists in the history of science. We had seen Jupiter before, sure. Fuzzy, blurry photographs from ground-based telescopes that showed a planet that looked like a giant angry marble with a red smear across its belly. But nobody truly understood what they were looking at. It was like staring at a painting from across a football field. You can see the colours, maybe a shape or two, but you miss the brushstrokes, the texture, the sheer violence of the artist's hand. Then came Voyager, and when those twin spacecraft started sending back their first real close-ups, we weren't just looking at a painting anymore. We were falling headfirst into the canvas. Voyager 1 was the first to break the silence. In March of 1979, it flew past Jupiter at a distance that, in cosmic terms, was practically a sneak peek. The spacecraft's cameras, primitive by today's standards but absolutely revolutionary at the time, began to snap images that would redefine our entire understanding of planetary weather. The Great Red Spot, which from Earth looked like a static, boring oval, suddenly exploded into a cauldron of chaos. The images revealed a storm so complex it looked like a living organism. You could see white, churning clouds that looked like whipped cream being stirred into a cup of black coffee. Brown filaments, long and twisted, were being sucked into the storm's core like strands of hair caught in a drain. And it wasn't just rotating. It was alive. It was pulsing and writhing and feeding on the atmosphere around it. For the first time, we saw that the red spot was not just a spot. It was a hurricane the size of 3 Earths, spinning in a direction that defied the logic of our own planet's storms. On Earth, hurricanes spin and die. On Jupiter, this thing just kept going, and it didn't care what we thought about it. But the real magic happened just a few months later, when Voyager 2 showed up in July of 1979. This was the follow-up act, and it was even more spectacular. Voyager 2 didn't just take still pictures, it took movies. Time-lapse sequences that, when stitched together, showed the Great Red Spot in motion for the first time in human history. Imagine being the first person to watch a storm that's been raging for centuries finally move. It wasn't just spinning in place. It was interacting with everything around it. The footage showed the red spot chewing up smaller storms that drifted too close, swallowing them whole like a cosmic Pac-Man. It showed bands of gas being stretched and torn apart as they brushed against the spot's outer edge. And then there were the white ovals. The Great Red Spot is not alone. Jupiter has a whole family of storms, and one of them, a white oval that would one day become famous as Oval BA, was caught on camera being drawn eastward by the spot's immense gravitational pull. It was like watching a tugboat get caught in the wake of a supertanker. The two storms were locked in a dance, a dynamic coupling that showed us, for the first time, that Jupiter's atmosphere was a deeply interconnected system. Storms don't just exist in isolation. They talk to each other. They push and pull and steal energy from one another. It was a revelation that would keep planetary scientists busy for decades. And then came the lightning. Voyager's instruments detected something strange happening on the night side of Jupiter. Flashes of light. Electrical discharges. Lightning, but not like anything we see on Earth. On our planet, lightning comes from water clouds. On Jupiter, the lightning was coming from deep within the atmosphere, from clouds made of water and ammonia, hidden beneath miles of hydrogen and helium. The data was tantalizing but maddeningly incomplete. The spacecraft could tell that lightning was happening, but it couldn't tell us how deep it was, how frequent it was, or how it was distributed across the planet. It was like hearing thunder rumble in the distance, but never seeing the storm. We knew something powerful was happening down there, but Voyager simply didn't have the tools to dig any deeper. It was a mystery that would have to wait for another generation of spacecraft. But the seeds were planted. Perhaps the most shocking discovery came when scientists started mapping the wind speeds. They looked at the cloud motions in the Voyager footage and did the math. What they found was absolutely insane. The jet streams that flank the Great Red Spot, those powerful currents of air that wrap around the planet at high latitudes, were travelling at speeds that nearly doubled the storm's own rotation. That means the red spot, as massive and powerful as it is actually a relative slowpoke compared to the winds that surround it. It's like watching a race car driver go 200 miles an hour, only to realise that the track itself is moving at 400 miles an hour. How is that possible? How can a storm survive inside a current that is moving faster than the storm itself? It defies terrestrial logic. And yet there it was, plain as day in the data. Then there was the heat. Voyager carried an infrared instrument, and when it looked at the Great Red Spot, it found something that turned the entire model of planetary meteorology on its head. The centre of the storm was warmer than its edges. Think about that for a second. On Earth, the centre of a hurricane is cold. It's the eye of the storm, a calm, cooler region surrounded by the raging eye wall. But on Jupiter, it's reversed. The core of the red spot is a hot spot. It's like the storm is generating its own internal heat, bubbling up from the depths of the planet. That warmth is what drives the storm's incredible longevity. It's not just sitting on top of the atmosphere, being pushed around by external winds. It's feeding from below. It has its own power source. And that right there is the single most important clue that would eventually lead to Juno's electrical discovery decades later. But let's not forget the cultural impact. Because science doesn't happen in a vacuum. When Voyager's images of the Great Red Spot hit the newsstands, they didn't just appear in scientific journals. They were splashed across the covers of Time magazine, National Geographic, and newspapers from New York to Tokyo. The image of that swirling, blood-red eye staring back at Earth from 250 million miles away became an instant icon. It was on posters in teenagers' bedrooms. It was the backdrop for science fiction novels. It was referenced in movies and TV shows. Jupiter's Great Red Spot wasn't just a scientific discovery anymore. It was a pop culture phenomenon. It became shorthand for the unknown, for the idea that there are still places in our own solar system that can truly terrify and amaze us. For a brief moment in the late 1970s, the entire world was obsessed with a storm on a gas giant. And that obsession, that collective sense of wonder, is what kept the funding and the public interest alive for the missions that would follow. And here's the kicker. The Great Red Spot is famous, but it is not unique. Voyager revealed that Jupiter is the most storm-rich world in the entire solar system. Dozens of long-lived oval storms were found scattered across the planet, some white, some brown, some red. They come in all sizes, from small swirls no bigger than Earth's continents, to beasts that could swallow our planet whole. Jupiter is a storm factory. It churns out these massive weather systems like a cosmic assembly line, and each one of them has its own personality, its own life cycle, its own way of interacting with the planet's ferocious atmosphere. The Great Red Spot just happens to be the oldest, the biggest, and the most famous. But it is far from the only monster lurking in those clouds. So there we were, at the end of the Voyager era. We had seen the storm. We had measured its winds, felt its heat, watched it eat its neighbours, and learned that it was not alone. But Voyager, for all its brilliance, was just a flyby. It was a sneak preview. It gave us the trailer, not the movie. We knew the storm was warm in the centre, but we didn't know why. We knew lightning was flashing below, but we couldn't see the source. We knew the winds were impossibly fast, but we couldn't understand the engine that fueled them. Voyager opened Pandora's box, but it only let us peek inside. The real work, the deep dives, the answers that would rewrite our understanding of how planets form, how they generate their own magnetic fields, and how they shape the very chemistry of the solar system, those would have to wait for the next generation. And that next generation, dear listener, came in the form of a little spacecraft named Galileo, and it was about to take a very, very different approach. And so, as the Galileo mission was rewriting the rulebook on what we thought we knew about the gas giant, another set of eyes was already hurtling toward the Jovian system. These eyes belonged to a spacecraft that was, in many ways, a ghost. It was a mission built on borrowed time, a traveller that had already completed its primary objective at Saturn and was now coasting through the void, looking for one last great adventure. That spacecraft was Cassini, and in December of the year 2000 it performed a flyby of Jupiter that was so meticulous, so obsessively detailed, it gave us a map of the planet so sharp it looked like you could reach out and touch it. Now you have to understand the sheer scale of this feat. Cassini was not designed for Jupiter, it was built for Saturn, but as it swung by the king of planets for a gravity assist, its operators decided to point every single instrument they had at the clouds below. The result? A staggering mosaic of 27,000 individual images. Think about that number for a second. 27,000. That was not a quick snapshot. That was a photographic assault on the planet's secrets. It produced the highest resolution global map of Jupiter ever created up to that point in history. Every swirl, every curl, every bruise-coloured storm that had ever been sketched by amateur astronomers was captured with a clarity that left scientists breathless. And what did they see? Well, the Great Red Spot was still there, of course, sitting in the southern hemisphere like a massive, unblinking eye. But Cassini's gaze was drawn to something else. Something that, for decades, had been living in the shadow of that giant. We are talking about the white ovals. For generations, astronomers had watched 3 distinct white oval storms churning away in a band just below the Great Red Spot. They were long-lived features, having persisted since the 1930s. For nearly 70 years, these 3 storms, given the charmingly bureaucratic names of BA, BC and D, had just been there. They were stable, they were white, and they were largely ignored. Why would they not be? Compared to the granddaddy of all storms, they looked like little puffs of cotton in a hurricane. But the universe, as it always does, was cooking up a surprise. The question on everyone's mind was this: What happens when you take three very old, very stable storms and force them to dance together? Around the turn of the millennium, right as Cassini was snapping those 27,000 pictures, the Hubble Space Telescope was watching these three white ovals do something they had not done in decades. They started to move, they started to drift, and then, in a gravitational ballet that took years to complete, they began to merge. Between 1998 and the year 2000, the Hubble team documented the process in excruciating detail. First, Oval BC swallowed Oval DE. It was a messy, swirling affair that looked like 2 drops of milk colliding on a hot skillet. Then, that newly combined storm started to close in on the last remaining independent oval, Oval BA. And in the year 2000, the merger was complete. Where 3 separate white storms had once stood, there was now one massive, churning pearly cloud complex. Oval BA was born, and the entire astronomical community held its breath. Why the excitement? Because Oval BA was now the second largest storm on the planet. The only thing bigger than it was the Great Red Spot itself, and that raised a terrifyingly beautiful possibility. Was Jupiter about to grow a second Great Red Spot? Was the planet, in its infinite complexity, replicating the very process that had created its most famous feature centuries before? We had a front-row seat to the birth of a potential monster. Scientists immediately began monitoring Oval BA with a level of attention usually reserved for the red spot itself. They watched its colour, its spin, its internal temperature. They wanted to know if it would stay white or if it would turn red. And for a few years, Oval BA was a good little storm. It was big, it was stable, and it was stubbornly white. It seemed content to be a large, pale copy of its predecessor. But then, in 2005, something snapped. Or rather, something blushed. Astronomers looking at Hubble images noticed a change. The core of Oval BA, which had been a pristine white for decades, began to take on a reddish tint. At first, it was subtle, a faint blush, but the colour deepened over the following months, spreading from the centre outward until the entire storm had a distinct reddish-brown hue. It was not as deep and vibrant as the Great Red Spot, but it was undeniably red. The storm had a new name and a new personality. The press, with their love for a good story, dubbed it Red Junior, or the Baby Red Spot. And the question shifted from will it turn red to what happens when the baby meets the parent. That answer came in the summer of 2008. It was an encounter that had been anticipated for years, a celestial close call that had astronomers scheduling telescope time from the deserts of Chile to the mountains of Hawaii. Oval BA, the Baby Red Spot, was drifting up toward the Great Red Spot. The two storms were on a collision course, or at least a very, very close flyby. On July 4th, 2008, they drifted within 1 storm diameter of each other. That is terrifyingly close. To give you a sense of scale, 1 storm diameter of the Great Red Spot is about the width of the Earth. So imagine a storm the size of our planet, passing within arm's reach of another storm that could swallow us whole. What happened next was a masterclass in planetary fluid dynamics. They did not merge, the marriage did not happen. Instead, they interacted. They pushed and pulled at each other like 2 titans, testing each other's strength. The gravitational influence of both storms warped their shapes. The Great Red Spot, for the first time in years, got a little bit ragged around the edges. Its perfect oval became slightly kinked. But the effect on Oval BA was even more dramatic. The close encounter stripped away the outer layers of the Baby Red Spot, distorting its shape until it looked like a squashed oblong blob. And then there was the colour change. The energy of the interaction, the shearing forces, the exchange of angular momentum. It did something to Oval BA's internal chemistry. When the storms finally separated and Oval BA drifted away, it was no longer the same reddish-brown colour it had been before. It had changed, it had deepened, it had become more saturated, it had become more red. The close encounter had supercharged its colour, making it look even more like its larger, older sibling. This was direct observational evidence that the colour of these storms is not a fixed property. It is dynamic, it is energetic, and it is deeply linked to the storm's activity and its interactions with the environment. So what did we learn from the story of Cassini, the white ovals, and the birth of the baby red spot? We learned that Jupiter is not a static museum of weather. It is a laboratory. The relationship between the Great Red Spot and oval BA is a perfect case study in storm dynamics. It teaches us that size is not everything, but it is a major factor in stability. The big one held its ground. The smaller one was bent, warped, and recolored. We learned that colour is a direct indicator of a storm's energy and depth. A pale white storm is one that is perhaps stable but quiet. A red storm is one that is active, deep, and pulling material from the darker complex chemical layers below. And crucially, we learned that these storms are not isolated actors. They feel each other. They push on each other. They change each other. There is a gravitational conversation happening between every swirl and curl on that planet. It was a stark reminder that on Jupiter nothing exists in a vacuum. Not even a storm that has been alive since the presidency of Franklin D. Roosevelt. And so, as Cassini continued its lonely voyage toward the ringed world, it left behind a map of a planet that was more alive than we had ever imagined. A planet where a baby storm could grow up, change colour, and challenge its parent for dominance. But of course, for every question answered, a dozen more were raised. What would happen to oval BA in the long term? Would it survive? Would it grow? Or would it, like so many storms before it, eventually be consumed by the monster that it had dared to dance with? To understand the Great Red Spot, you have to first accept a truth that feels almost alien to us. Jupiter has no ground. There is no surface to land on, no continent for this storm to scrape against, no mountain range to deflect its winds. The Great Red Spot is not anchored to anything solid. It exists within a fluid envelope, a vast layered ocean of atmosphere that stretches for tens of thousands of kilometers into the planet's interior. And that changes everything about how we have to think about it. Let's start at the top, because that's where our eyes naturally go. The visible cloud tops of Jupiter, the swirls of orange, white, and brown that paint the planet's face, are made of frozen ammonia crystals. It is a world of bitter cold up there. The temperature hovers around minus 145 degrees Celsius. That is cold enough to freeze carbon dioxide out of the air. Cold enough to make the most inhospitable winter on Earth feel like a tropical paradise. And yet, that is just the skin of the planet. Beneath those frozen ammonia clouds, the atmosphere gets stranger. You descend through a layer of ammonium hydrosulfide clouds. That is a fancy way of saying it smells like rotten eggs and ammonia mixed together. A chemical soup that would be toxic to anything we know. Below that, you hit the water clouds. Yes, there is water on Jupiter, huge amounts of it, but it's not a liquid ocean you could swim in. It's more like a deep, slushy, high-pressure fog, a region where the atmosphere is so thick and hot that water exists in a state that is neither fully gas nor fully liquid. And then, as you keep going, things get genuinely wild. The pressure and temperature rise so dramatically that the hydrogen around you starts to behave differently. First, it becomes a liquid. Then, deeper still, it gets squeezed so hard that the electrons get stripped away from the atoms. You have entered the realm of metallic hydrogen. This is not something we have on Earth. It is a state of matter that only exists under immense gravitational pressure. A fluid that conducts electricity, a liquid metal flowing deep inside the planet. That metallic ocean is what generates Jupiter's absurdly powerful magnetic field, the strongest of any planet in the solar system. Now, here is where the temperature profile becomes almost unbelievable. At the cloud tops, it's minus 145. But the deeper you go, the hotter it gets. And it does not just get a little warm, it gets hot. The temperature rises steadily, passing the freezing point of water, passing the boiling point, passing the melting point of lead. And then it keeps going. By the time you approach the core, the temperature is estimated to be over 20,000 degrees Celsius. That is hotter than the surface of the Sun. Jupiter's core is a place where the boundaries between gas, liquid, and solid completely break down, a bizarre, supercritical soup of material crushed into a state we cannot even properly simulate. But here's the thing that really matters for the Great Red Spot. The entire weather layer of Jupiter, the part of the atmosphere where all those beautiful bands and storms live, is far deeper than anyone ever guessed. Before NASA's Juno spacecraft arrived, most scientists assumed that the colourful bands we see were just a thin skin, maybe a few 100 kilometres deep. But Juno measured the planet's gravity field with incredible precision, and what it found was staggering. Those atmospheric bands, the jet streams that create the striped appearance of the planet, extend downwards for at least 3,000 kilometres. That is deeper than the entire radius of Earth's core. Jupiter's weather is not a surface phenomenon. It is a deep, massive churning system that involves a colossal fraction of the planet's total mass. Think about that. The Great Red Spot is not just a surface storm. It is a structure that reaches thousands of kilometres into the planet's interior. It is fed by energy and gas from these unimaginable depths. And speaking of energy, Jupiter has a secret. It radiates more heat into space than it receives from the Sun. That is not normal for a planet. Earth gets nearly all its energy from the Sun. But Jupiter, for all its distance from our star, is still glowing hot from its own formation. It is still contracting, slowly, very slowly, collapsing under its own immense gravity, and that gravitational contraction generates heat. This internal energy is a constant, driving force. It fuels the jet streams. It stirs the deep atmosphere, and it provides a steady supply of power to the Great Red Spot, allowing it to persist for centuries, laughing at our human definitions of weather. Now place the storm within its environment. The Great Red Spot lives at a specific latitude, roughly 22 degrees south of Jupiter's equator. It sits in a slot between two powerful jet streams. One flows to the east, the other to the west. These are not gentle breezes. We are talking about the fastest persistent winds in the entire solar system. In the strongest belts, the winds can reach 620 kilometers per hour. That is nearly twice the speed of the most powerful tornado ever recorded on Earth. And these winds blow continuously, year after year, century after century. The Great Red Spot is caught between these two opposing currents, like a spinning top balance between two fan blades. It has found a gravitationally stable configuration. It is a physics-driven structure that operates on principles far beyond our Earth-based intuition. Here on Earth, a storm is a temporary disturbance. It forms, it rages, it moves, and eventually it dissipates when it runs out of energy or hits land. But on Jupiter, there is no land. The storm is not fighting friction from the ground. It is not being shredded by mountains. It exists in a perfectly fluid environment, supported by the deep, warm, energetic atmosphere below it. The Great Red Spot is not a visitor to Jupiter's atmosphere. It is a part of it. It is an expression of the planet's internal dynamics, a vortex that has locked itself into a stable orbit within the giant planet's fluid body. And that changes the question entirely. We are not looking at a weather event in the earthly sense. We are looking at a persistent structure, a feature that is as fundamental to Jupiter as the bands themselves. It is a window into the deep interior, a visible marker of the immense forces that shape the largest planet in our solar system. The storm swims in an ocean of gas and liquid metal, and that ocean is alive with energy, pressure, and motion that we are only beginning to understand. So when you look at that swirling red eye, remember that you are not just seeing a storm. You are seeing the face of a planet that is still breathing, still contracting, still radiating its birth heat into the cold void of space. And the Great Red Spot is simply its most prominent sigh. And that sigh, that ancient exhale from Jupiter's depths, is now whispering secrets we are only beginning to decode. But here is the uncomfortable truth we have to confront. The Great Red Spot is dying. Or at least, it is changing in ways that force us to ask whether we are witnessing its final act, or simply the next stage in a cycle we have barely begun to understand. For decades, scientists have watched this colossal storm shrink. When Giovanni Cassini first sketched it in the 1600s, some estimates suggest it was wide enough to swallow 3 Earths side by side. By the time the Voyager spacecraft flew past in the late 1970s, it had already diminished to about 2 Earths across. Today it has shrunk to barely 1.3 Earth diameters. That is not just a slow drift. It is a dramatic, measurable collapse. This has sparked a fierce debate within planetary science, pitting two very different models against each other, each with implications for everything we think we know about gas giant meteorology. Model 1 argues for equilibrium. The idea is that the Great Red Spot is not disappearing, but is settling into a stable size, a sweet spot where the forces that sustain it balance perfectly against those that erode it. According to this model, the storm will continue to shrink, but only until it reaches a critical threshold, perhaps around Earth's diameter. Once it hits that size, the internal dynamics stabilize. The vorticity, the rotational energy inside the storm, locks into a configuration that resists further dissipation. Think of it like a spinning top that wobbles violently at first, then settles into a smooth, steady spin. The spot would become smaller, but it would remain a permanent feature of Jupiter's atmosphere for centuries or even millennia. Model 2 is far more alarming. It suggests that the Great Red Spot is approaching a point of no return. Below a certain size threshold, the storm's internal structure becomes unstable. The surrounding jet streams, those powerful east-west winds that act as containment walls, begin to shear it apart from the outside. Once the spot falls below a critical diameter, the dissipation accelerates exponentially. It would not just fade away slowly, it would vanish within a few decades, like a whirlpool in a draining bathtub that suddenly collapses in on itself. Under this model, the Great Red Spot could be gone before our grandchildren are old enough to read about it in history books. For a long time, these two models were locked in a stalemate. The observational data was too sparse to favour one over the other. Then came a study published in 2023 that tilted the scales in a fascinating direction. Researchers tracking the storm's size, using decades of Hubble Space Telescope imagery, noticed something unexpected. The shrinkage rate, fairly constant since the 1990s, appeared to have slowed down significantly around 2020. The storm seemed to be approaching a plateau, losing area much more slowly than before. This does not prove the equilibrium model is correct, but it gives it a serious boost. It suggests the storm might be approaching that stable configuration rather than accelerating toward oblivion. But here is the catch. We still do not know where that threshold lies, or even if it truly exists. We are watching a cosmic event unfold in slow motion, but our instruments can only see the surface. And that is the fundamental problem. We have stared at the Great Red Spot for nearly 400 years, and we still do not know how deep it goes. Is it a shallow weather phenomenon, a hurricane extending only a few dozen miles into the atmosphere? Or is it a deep-rooted column of gas extending thousands of miles downward, anchored to Jupiter's internal heat? The Juno spacecraft gave us our first real hints. Its gravity measurements suggested the storm's roots go deeper than we ever imagined, perhaps as far as 300 miles. But beyond that, the data gets murky. We need to send a probe into that storm, one that can survive crushing pressures and transmit data back before being vaporized. That is where the proposed Jupiter Atmospheric Probe mission comes in. This joint concept between NASA and the European Space Agency is the spiritual successor to the Galileo probe that plunged into Jupiter in 1995. But that old probe was a pioneer, not a specialist. It entered at a shallow angle, hit an unusually dry region of the atmosphere, and only survived to about 90 miles before the pressure crushed it. The new mission would be designed differently. It would be a dedicated entry probe built specifically to target the Great Red Spot. It would enter at a steeper angle, use a more robust heat shield, and carry instruments capable of functioning at pressures hundreds of times greater than Earth's surface. If all goes well, it would send back a vertical profile of the storm, measuring temperature, composition, wind speeds, and cloud density, all the way down to its deepest roots. That data would finally settle the debate between the equilibrium model and the dissipation model. It would tell us whether the storm is a shallow puddle or an abyssal ocean, but we do not have to wait for a space probe to make progress. Closer to home, the Extremely Large Telescope, or ELT, is under construction in the Atacama Desert of Chile. When it comes online later this decade, It will be the largest optical telescope ever built, with a mirror over 39 meters across. That is big enough to resolve details on Jupiter that currently only Hubble can see, and it will do so from the ground, continuously, without the scheduling constraints of a space telescope. For the first time, we will be able to monitor the Great Red Spot in high resolution for years on end, watching every twitch, every colour change, every subtle shift in its internal turbulence. The ELT will be our constant eye on the storm, providing the long-term dataset that theoretical models desperately need. And here is where things get really interesting. This is not just about Jupiter. It is about every hot Jupiter we have discovered orbiting distant stars. These exoplanets, many of which are tidally locked and bathed in extreme radiation, are expected to host colossal storms of their own, storms that may dwarf even the Great Red Spot. But we cannot see those storms directly. The light from those planets is too dim, too blurred by the glare of their stars, so we have to infer their behaviour through indirect measurements, such as how their atmospheres redistribute heat from the day side to the night side. A giant storm on a hot Jupiter acts like a planetary-scale heat pump, dragging energy around the globe and affecting the planet's overall energy budget. If we misunderstand how storms behave on our own gas giant, we will inevitably misinterpret data from these distant worlds. The Great Red Spot is our Rosetta Stone. Deciphering it will unlock the atmospheric physics of countless exoplanets. And that brings us to the philosophical heart of the matter, the part that keeps planetary scientists up at night. The Great Red Spot has been staring at us for longer than any human civilization has existed. The ancient Chinese astronomers may have glimpsed it. Galileo missed it. Cassini recorded it. The storm was there when Rome fell, when the pyramids were built, when the first humans left Africa. It has outlasted every empire, every philosophy, every religion that has tried to explain it. Yet after all that time, after all our telescopes and spacecraft and computer models, the most unsettling truth from Juno is this: we still do not fully understand why it exists. We do not know why it has lasted so long. We do not even know what it is truly made of. We call it a storm, but that is a human word, a limited label for a phenomenon that defies our categories. It might be a vortex, a standing wave, a convection cell, or something we have not even conceived of. Every time we think we have it figured out, Jupiter throws a curveball. The colour has shifted from brick red to pale salmon and back again. The shape has morphed from a long oval to a more circular blob. The internal winds have accelerated, even as the overall storm has shrunk. It is almost as if the storm is alive, adapting, resisting our attempts to pin it down. And perhaps that is the most profound lesson of all. We are not just studying a weather system. We are confronting the limits of human knowledge, face to face with a mystery that may outlast us the same way it has outlasted every generation before us. The Great Red Spot will continue to churn, long after we have turned away, long after our instruments have rusted, and our books have crumbled. It will be there, a red eye in the sky, watching the galaxy drift past, indifferent to our curiosity, our theories, our desperate need to understand. And that, more than any measurement or model, is the truth that humbles us every time we look up at Jupiter. And so we circle back to where we began, standing on the edge of the abyss, staring into a storm that doesn't care if we exist. The Great Red Spot is more than a weather event. It is a monument to the scale of the universe's indifference. It is a phenomenon that forces humility, not because it is violent, not because it is beautiful, but because it simply outlasts us. This storm is older than the science we use to study it. It was already spinning when Galileo first pointed his primitive telescope at the sky, a smear of red he could barely make out. It was spinning when Isaac Newton was formulating gravity, when the steam engine was being built, when our entire understanding of the physical world was being rewritten from scratch, and it will still be spinning long after we are gone. We have learned incredible things. Juno's dive into the abyss revealed routes that plunge 500 kilometers deep. That is not a surface feature. That is a wound in the planet's atmosphere, a chasm where hydrogen and helium compress into something alien. We discovered an internal chemical sunburn, where organic compounds are cooked by ultraviolet light, creating that deep crimson colour, we uncovered symbiotic jet streams, invisible rivers of gas that feed the storm energy from the planet's interior. And most astonishing of all, we found that the storm is a self-sustaining heat engine. It does not rely on the sun. It generates its own power. It eats its own waste. It is a closed loop of chaos that has been running for perhaps 400 years, maybe more, with no sign of stopping. But here is the part that should make you pause. Think about the brevity of human observation. We have been watching this storm with spacecraft for only a few decades. A blink, a whisper. We have sent probes like Voyager, Galileo, Cassini in passing Juno orbiting. And in that time, we have seen the storm shrink. We have seen its colour shift. We have seen it wobble and pulse and shed tendrils of gas. But we have not seen it die. And we will not. The storm will likely outlast our civilization. It might outlast our species. Imagine that. Long after every city has crumbled, every language has been forgotten, every satellite has rusted in orbit, the great red spot will still be there, circling the planet every 6 days, churning its eternal fury, completely unaware that we ever existed. That is not a morbid thought. That is a liberating one. It reminds us that the cosmos does not owe us an explanation. It simply is. And our job, as curious creatures gifted with consciousness, is to keep asking questions even when the answers are terrifying or humbling. That is the heart of exploration. That is the fire that drives every scientist, every engineer, every dreamer who looks up at the night sky and wonders. And if you want to keep exploring these mysteries, to watch the storm's evolution in real time, to understand the universe's hidden engines, then subscribe to This Is Space. Every week we bring the cosmos closer. Press the bell icon and join us for the next revelation, because this is not a one-time story. The great red spot is still changing. Juno is still sending data. There are still secrets buried in those clouds that we have not yet decoded. And when the next discovery breaks, when we find something even stranger inside that crimson eye, you will want to be here. You will want to hear it first. Think about it. We have already seen things that would have seemed like magic 100 years ago. We have mapped the surface of Mars. We have landed on an asteroid. We have flown through the rings of Saturn. And now we are probing the depths of a storm that swallows planets whole. What comes next? What new wonder is waiting just beyond the horizon? The universe is not done revealing itself, and neither are we. So let the storm spin, let it rage, let it outlast every monument we ever build, because that is its nature. It is the void made visible, a chunk of chaos that refuses to die, and we, for all our fragility, have been lucky enough to witness it. We have seen the Great Red Spot as more than a legend. We have seen it as a scientific marvel, a weather system that defies everything we thought we knew about planetary dynamics. We have seen it as a mirror, reflecting our own limitations back at us, and we have seen it as a promise that there is always more to learn. The storm that swallowed Earth is still spinning, and we are still watching. Now you know what is inside that spot. You know about the 500-kilometre routes. You know about the chemical sunburn. You know about the heat engine that runs on nothing but its own momentum. And you know that this storm will outlast us all. That is not a defeat. That is an invitation. An invitation to keep looking, to keep questioning, to keep subscribing to a channel that takes you closer to the edge of understanding. So hit that subscribe button, hit the bell, and let us face the void together. Because the cosmos is vast and violent and beautiful, and we have only just begun to scratch the surface. The Great Red Spot is still holding secrets, and when it finally gives them up, you will be here to hear them. You will be part of that moment. That is the power of curiosity. That is the power of this community, and that is why we keep coming back week after week, to stare into the face of a storm that will never, ever stop. But consider this. The Great Red Spot is not just a storm, it is a record of deep time. Every swirl of gas carries the fingerprint of centuries. Every eddy and tendril is a snapshot of forces that have been in play since before the Industrial Revolution, before the age of exploration, before the invention of the printing press. When you look at that storm, you are looking at history. You are looking at a process that has witnessed the entire arc of modern humanity unfold beneath its gaze. It saw the rise and fall of empires. It saw wars and discoveries, and all the little dramas we call progress. And through it all, it just kept spinning. That is not a metaphor. That is physics. That is the relentless march of angular momentum. A force that does not care about our calendars or our milestones. The storm is a physical object that has existed for hundreds of years, but we are the first generation to truly understand what it is. We are the first to map its depths, to measure its heat, to watch it breathe. We are living in a golden age of planetary science, and the Great Red Spot is our greatest teacher. Every byte of data that Juno sends back is a lesson in humility, a reminder that the universe operates on scales and timescales that dwarf our own. And yet we persist. We build better instruments. We launch better spacecraft. We ask better questions. That is the human spirit. That is why we are here on this channel at this moment together, staring into the face of a storm that will outlast us. And that is exactly why we will never stop.